What if I told you that the Milky Way is not just drifting through space, but being pulled by something we can't fully see or even comprehend? For decades, astronomers have been puzzled by this mysterious pull, a gravitational force not only affecting our galaxy, but thousands of others as well. As for the source of this force, it's hidden behind a thick veil of cosmic dust in a region we've only just begun to explore. And yet this invisible hand has been shaping the movement of galaxies for billions of years, guiding them along vast, unseen paths carved into the very fabric of the cosmos. It's as if our galaxy has been caught in a grand celestial current, a hidden stream of galaxies moving toward a single point, a point known to scientists as the Great Attractor. But that's just the beginning of a much larger mystery. In 2014, researchers discovered something even more astonishing. The Milky Way, along with tens of thousands of nearby galaxies, is part of a much larger structure, a supercluster spanning over 500 million light-years. But even Laniakea, as vast as it is, may not be the end of the story. Recent data suggests that our galaxy may be heading far beyond, to an even greater cosmic basin, a colossal structure that we are only beginning to understand. Where is the Milky Way really headed, and what awaits us at the end of this journey? It was 2014. Scientists stood on the brink of a discovery that would turn our understanding of the universe upside down. For years, we thought that the Milky Way was part of the local group of galaxies, relatively isolated, drifting in space. But everything changed when researchers began mapping galaxy movements in a new way, uncovering an unexpected and massive structure, the Laniakea Supercluster. The key to this discovery lay in what's now known as redshift. As we look at distant galaxies, their light shifts toward the red end of the spectrum as they move away from us. This is directly related to the expansion of the universe. But that's not the whole story. Galaxies also have their own peculiar velocities, unique motions that don't conform solely to the process of universal expansion. These peculiar motions tell us about something really major. They show us where galaxies are headed. By observing these redshifts and combining them with distance measurements, astronomers were able to create a map of galactic flow. In essence, it was a map of how galaxies move through space over time. And this is where the real revelation occurred. As they studied the data, researchers noticed something incredible. The Milky Way wasn't just aimlessly drifting in space. It was part of a massive cosmic structure, interconnected with nearly 100,000 other galaxies. This structure became known as the Laniakea Supercluster. But what exactly is a supercluster? Imagine hundreds of thousands of galaxies, bound together by gravitational ties and moving together as part of an enormous cosmic current. Laniakea spans more than 500 million light-years, an area so vast it's difficult to even comprehend. And yet, the Milky Way, our solar system, and even our Sun are mere specks in this grand flow. But Laniakea is not just a random cluster of galaxies. It's something far more complex, and it's what we now call Basins of Attraction, or BOA. A BOA is like a gravitational well, an area where galaxies are pulled toward a central point by a force we can't directly see. In the case of Laniakea, all the galaxies that are part of this supercluster are being drawn to a specific point in the cosmic web, a point where gravity dominates, and those very streams of matter converge. The discovery sparked new research. If Laniakea is just one basin of attraction, could there be others? And if so, where are they? As scientists continued working on this, they realized that the cosmic web A vast network of galaxies, clusters, and voids stretching across the universe was even more complex than they had imagined. The concept of basins of attraction took on new significance. Each of these basins represents a region where gravity has shaped the flow of galaxies over billions of years. And our galaxy, the Milky Way, is just one of many, swept up in these cosmic currents, heading toward places still unknown. But the question wasn't just where the Milky Way was headed. This was the first step toward uncovering the true nature of our cosmic surroundings. In search of the true shape and movement of our universe, scientists rely on vast data sets, catalogs. Today, one of the most powerful tools in this type of work is something called Cosmic Flows 4. Cosmic Flows 4, or CF4, is the largest and most detailed collection of its kind. It contains data on over 38,000 galaxy groups, each representing a massive cluster of stars, planets, and dark matter. These groups span the entire local universe, reaching distances of over 400 million light-years. But the interesting thing about this data lies in the fact that it's not only telling us where these galaxies are, it tells us something much more important: where they are moving. But to understand this, we need to look beyond simple positions. We need to measure the so-called peculiar velocities. The peculiar velocity of a galaxy is its individual motion relative to the expansion of the universe. Each galaxy is moving away from us due to this expansion, but at the same time, they have their own unique motions. They're pulled by the gravitational attraction of nearby structures, drifting toward massive areas of gravity. By measuring these velocities and comparing them with redshift data, scientists can create a map where galaxies are moving. Essentially, this allows us to reconstruct the flow of matter in space, revealing hidden gravitational wells. But measuring these peculiar velocities isn't easy. The universe is a noisy place, and the data collected from galaxies is full of uncertainties, errors in distance, errors in velocity. To get a clear picture, scientists needed a new approach, and this is where advanced algorithms come into play. One of the most powerful tools used to map these basins is the Hamiltonian Monte Carlo method, or HMC. This advanced algorithm models the motion of galaxies by taking into account both the known data and the associated uncertainties. By running thousands of simulations, HMC creates a probabilistic map of where galaxies are most likely to be, essentially creating a set of possible universes, all of which match the data we have. The advantage of this method lies in its ability to account for the complexity of cosmic flows. Each galaxy group is influenced not only by its closest neighbors, but also by structures of a much larger scale. By simulating all these influences together, HMC gives us a much clearer view of the vast web of interactions shaping our universe. Using CF4 and the HMC algorithm, astronomers have been able to map not just individual galaxies, but entire clusters, filaments, and voids, the complex architecture of the cosmic web. And more importantly, they've been able to identify the aforementioned basins of attraction, the gravitational centers toward which all matter in these regions is drawn. And even the Milky Way, located deep within the Laniakea supercluster, is part of this massive flow, moving toward a distant and mysterious center of attraction. But the story doesn't end there. The deeper we look, the larger and more tangled the universe becomes. As scientists examined the data from Cosmic Flows 4, a broader picture began to emerge. It turned out that Laniakea is just one component of a much larger cosmic flow. All the galaxies within Laniakea, including the Milky Way, are not only moving toward the Great Attractor, but are also being drawn further toward an even larger structure known as the Shapley Supercluster. Discovered in the early 20th century, Shapley is a gravitational giant. It's one of the largest and heaviest structures in the nearby universe, spanning more than 650 million light-years. Within it are hundreds of galaxy clusters, and the total mass is so enormous that it pulls in galaxies that are far beyond its boundaries, including our own. Using CF4 data, recent studies have confirmed what astronomers have long suspected. The Shapley Supercluster is not just a neighbor to Laniakea, it is a much larger gravitational basin. In fact, there's compelling evidence that the Milky Way, Laniakea, and the Great Attractor are all being pulled under the far-reaching influence of Shapley. But even Shapley, as enormous as it is not the final stop in the journey across cosmic structures. Beyond it lies something even more grand, something that surpasses both Shapley and Laniakea combined. And this is the Sloan Great Wall. First discovered in the early 2000s, the Sloan Great Wall is the largest known structure in the local universe, stretching across 1.5 billion light-years. For comparison, the Sloan Great Wall is more than twice the size of both Shapley and Laniakea combined. The wall represents the largest BOA we've ever identified. It's a gravitational hub so massive that it influences galaxies and superclusters millions of light-years away. While Shapley is pulling in our galaxy and Laniakea, the gravitational influence of Sloan stretches even further, shaping the movement of galaxies on truly cosmic scales. But what makes these structures even more intriguing is how they fit into the larger puzzle of the cosmic web. Shapley, Sloan, and Laniakea are connected by invisible threads, vast highways of dark matter that stretch across the universe, guiding the movement of galaxies and clusters. Just as rivers flow to the ocean, galaxies and superclusters are drawn along these threads, converging at the deepest gravitational wells, the basins of attraction. And while we now understand that the Milky Way is in the midst of a long journey toward Shapley, the Sloan Great Wall serves as a reminder that the universe is always grander than we imagine. The discovery of these massive structures raises new questions. What other giant basins of attraction may lie beyond this wall? How do these vast regions of gravitational pull influence the evolution of galaxies over billions of years? And perhaps most intriguingly, what does this mean for the ultimate fate of our galaxy and the universe as a whole? However, even these colossal discoveries are just the beginning. There are still vast regions of space we've barely explored. And even the structures we've uncovered are only part of a much larger cosmic puzzle. As we venture deeper into space, we encounter gaps in our knowledge, places where even our most advanced instruments can't make observations. One of the most significant obstacles lies right behind the Milky Way, in a region known as the Zone of Avoidance. This area is filled with gas and dust, making it nearly impossible to observe the galaxies and structures hidden beyond it. Like a curtain drawn across part of the universe, it blocks our view of critical regions of gravitational influence. But as we look toward the future, a new era of discovery is on the horizon, one that promises to lift this cosmic veil and reveal more of the universe than ever before. Missions like Euclid and the completion of the Vera C. Rubin Observatory will allow us to see farther, deeper, and with greater precision than ever before. Euclid, set to create an unprecedentedly detailed map of the universe, will trace the distribution of dark matter and expose the hidden foundations of the cosmic web. It will give us a new perspective on the mysterious dark energy driving the expansion of the universe, and with it a clearer understanding of the forces shaping the fate of galaxies. Meanwhile, the Rubin Observatory will scan the night sky, creating a time-lapse of the universe in motion. By capturing the position and movement of billions of galaxies, Rubin will help us track cosmic flows in real time, refining our understanding of how galaxies, like the Milky Way, move through the cosmic web. It will fill in the gaps left by the Zone of Avoidance and likely reveal new basins of attraction that we haven't come across yet. But it's not just about discovering new structures. These tools will also help us understand the fate of our own galaxy. By mapping the flow of galaxies today, We may one day predict where these streams in the cosmic web will lead and how it will evolve over the next billions of years. What lies beyond the zone of avoidance? What other massive structures are waiting to be discovered? As we ponder these questions, we continue our journey into infinity, deeper toward the colossal Sloan Great Wall. With each new wave of data, the veil lifts a little more, and the mysteries of the cosmic web are gradually revealed, bringing us closer to understanding the true scale of a universe far larger and more interconnected than we could have ever imagined. In 1977, humanity embarked on one of its most daring journeys, launching 2 intrepid explorers into the great unknown. These were not astronauts, but the Voyager spacecraft, twin probes designed to push the boundaries of our cosmic backyard. Created by the hands of dreamers and inspired by the dreams of scientists, Voyager 1 and Voyager 2 were designed to fly to the stars. Their mission was not just to explore, but to introduce the inhabitants of the pale blue dot to the outer giants of our solar system. Armed with a gold plate, a time capsule that captures the essence of humanity, these silent ambassadors carried the sights and sounds of Earth, a message to the cosmos. We are here. We are exploring. We are Voyager. While we stood on the threshold of the unknown, the Voyagers continued and continue their lonely journey through the interstellar void. What mysteries have they uncovered? What stories of endurance and discovery are captured in their journey? And most importantly, will they still be able to discover some new worlds? Join our Voyager saga, a story of adventure, resilience, and humanity's relentless pursuit of knowledge. In the sweltering summer of 1977, a cosmic opportunity loomed on the horizon. The planets of our solar system were aligning in a way that happens only once every 176 years. This rare celestial event opened the way to the unknown and gave us a chance to embark on a grand journey to the outer planets. Using this happy coincidence, NASA engineers and scientists conceived of a mission in which 2 probes would slingshot from planet to planet, using the gravitational pull of each to propel them farther into the depths of space. The technological marvels that were Voyager 1 and Voyager 2 were equipped with the most advanced instruments of their time. From imaging systems capable of capturing Jupiter's swirling storms to magnetometers designed to study Saturn's magnetic fields, these spacecrafts were to rewrite our understanding of the solar system. But the journey to the launch pad was fraught with challenges, budgetary constraints, technological hurdles, and the boldness of the mission objectives pushed the team to the limit. Every component of the spacecraft had to be painstakingly tested, every system optimized for the rigors of space. As the launch dates approached, the excitement was palpable.
3, 2, 1. MDS, we have ignition, we have a liftoff.
Soaring into the skies, these twin messengers carried with them the hopes and dreams of all mankind, embarking on a journey that would forever change the way we think about the cosmos. When Voyager 1 and Voyager 2 traveled beyond the asteroid belt, they were greeted by the colossal presence of Jupiter, the gas giant that gravitationally dominates our solar system. These encounters set in motion a series of groundbreaking discoveries that would overturn our view of the outer planets. Armed with a host of sophisticated instruments, the probes peered into the planet's turbulent atmosphere, revealing the dynamic and violent nature of its storms. The imaging science system, a key component of Voyager's arsenal, captured stunning details of the Big Red Spot, a storm larger than Earth itself, and revealed never-before-seen features. But perhaps one of the most unexpected discoveries was the existence of Jupiter's thin ring system, a ghostly band of dust and particles girdling the planet. This discovery, made possible by the ship's photopolarimeter, disproved the notion the rings were a feature exclusive to Saturn. Among Jupiter's moons, Io stood out for its fiery temperament. The observations revealed a world with volcanic activity, the first time such phenomena have been observed outside of Earth. Moreover, Io is the most volcanically active body in our system, its surface forever changing under the inexorable forces of its interior. Images of towering plumes and lava flows have changed our understanding of geologic processes in the solar system. As the Voyagers continued their journey to Saturn, unprecedented beauty awaited them. The complex and intricate structure of Saturn's rings came into view, and the probe's cameras captured the subtle interplay of light and shadow among the countless ice particles. The scientific instruments aboard the spacecraft, especially the radio system, played a crucial role in studying the composition and dynamics of Saturn's rings. The data collected revealed the complex structure of the rings, including the mysterious gaps and braids phenomena whose formation continues to intrigue scientists to this day. Titan, Saturn's largest moon, was another highlight of the mission. Shrouded in a thick atmosphere, Titan was a world of mystery, its surface hidden from view. However, thanks to the ingenuity of Voyager's instruments, glimpses of this mysterious moon suggested the presence of liquid hydrocarbon lakes and a complex weather system, sparking curiosity and speculation about the possibility of life on it. The Voyager 1 and Voyager 2 encounters with Jupiter and Saturn have not only expanded our knowledge of the hot gas giants, but have also opened new frontiers in the exploration of the outer solar system. In the cold and distant reaches of our solar system, Voyager 2 set out for a solitary encounter with Uranus, the enigmatic ice giant. This historic encounter in January 1986 offered a glimpse of a world that had previously been just a pale blue dot in Earth-based telescopes. Uranus has presented an enigma to scientists with its peculiar tilted axis lying almost parallel to the plane of the solar system. This unusual orientation, with poles that alternately bask in the sun and languish in decades of darkness, has a profound effect on the planet's weather and atmospheric dynamics. As Voyager 2 approached, its instruments, including the narrow-angle imaging science system camera, began to capture unprecedented images of Uranus's atmosphere and its suite of moons and rings. The pale blue color of Uranus hid the complex structure of the atmosphere. Faint bands of clouds and previously invisible rings girdling the planet. One of the most striking discoveries was the nature of Uranus's magnetic field, revealed by the spacecraft's magnetometers. Unlike the Earth, whose magnetic axis coincides exactly with the axis of rotation, Uranus's magnetic field was found to be significantly displaced and tilted, suggesting a complex and possibly multi-layered internal structure. Leaving Uranus behind, Voyager 2 continued its journey to Neptune, the most distant of the known planets. In August 1989, mankind saw Neptune for the first time up close. A dynamic and turbulent world, at the center of which was the Great Dark Spot, a storm the size of the Earth. Neptune's atmosphere, buffeted by supersonic winds, paints a portrait of a planet alive with weather disasters. The spacecraft and its suite of instruments have delved into the mysteries of these winds, capturing the movement of cloud formations and the complex pattern of Neptune's faint rings. Among Neptune's moons, Triton stands out for its retrograde orbit and geologically young surface. Voyager 2 images of Triton showed a frozen landscape dotted with geysers spewing nitrogen gas and dust into space, hinting at a geologically active interior. Voyager 2's encounter with Uranus and Neptune have expanded the frontiers of our knowledge, revealing the diversity and dynamism of the outer planets. These fleeting visits have provided a treasure trove of data that continues to influence our understanding of the icy giants of the solar system. Moving farther and farther away with limited resources, mission controllers face the difficult question of which instruments should be left operational. To extend the life of the mission, non-essential systems, including the camera, were planned to be shut down permanently. But in a moment that epitomized the human spirit of exploration and reflection, astronomer Carl Sagan proposed a bold idea. Before the camera goes silent forever, he suggested that Voyager 1 take one last picture of Earth, a farewell shot of our home planet from the edge of the solar system. On February 13, 1990, the spacecraft warmed up its cameras for 3 hours. The spacecraft's science platform then took a series of images from a distance of about 4 billion miles that would later be combined into a mosaic of the solar system. Among the myriad scientific achievements, it was Voyager 1's gaze toward its home planet that captured the collective imagination of humankind. That pale blue dot is a testament to our insignificance in the vast expanse of space and a poignant reminder of our shared responsibility to preserve and protect the only home we have ever known. In an odyssey that stretches beyond the bounds of human perception, Voyager 1 and Voyager 2 traveled beyond the confines of our solar system, traversing the vast, uncharted territories of interstellar space. This monumental passage marked the first time humanity had traveled beyond the heliopause, the boundary where the sun's influence wanes and the mysteries of the cosmos are fully revealed. The heliopause is the extreme boundary of the solar zone, or domain, where the solar wind, a stream of charged particles emanating from the sun, meets the interstellar medium, the matter that fills the space between the stars in our galaxy. At this boundary, the external pressure of the solar wind is balanced by the internal pressure of interstellar gas and magnetic fields, creating a turbulent region that marks the end of the sun's influence. When Voyager 1 approached this boundary in August 2012, it became the first man-made object to cross interstellar space, providing scientists with direct measurement of the boundary for the first time. At that point, the instruments aboard the spacecraft, though developed in the 1970s, continued to transmit invaluable data back to Earth, recording a sudden decrease in solar wind particles and a corresponding increase in high-energy cosmic rays from outside our solar system, increasingly revealing the history of our universe. Voyager's journey beyond our solar system has not only expanded our understanding of the universe, but it's also paved the way for future endeavors in the never-ending quest to explore space. Their legacy is captured in the vast amount of data about the outer planets, their moons, and the heliosphere, and continues to be a cornerstone for scientific research, influencing the study of fields ranging from planetology to astrophysics. These missions have provided insights into the dynamics of planetary atmospheres, the structure of rings, and the nature of magnetic fields, setting the stage for subsequent missions. In the spirit of Voyager's pioneering voyage, subsequent missions have been designed to delve deeper into the mysteries uncovered by the twin spacecraft. For example, the Cassini-Huygens mission expanded our knowledge of Saturn by deeply analyzing the planet's rings, moons, and atmosphere. Similarly, the Juno mission looked beneath Jupiter's clouds, revealing the secrets of its internal structure and magnetic field. Looking to the future, the scientific community is clamoring for dedicated missions to Uranus and Neptune. These proposed missions are aimed at a comprehensive study of the icy giants, exploring their unique atmospheres, complex ring systems, and diverse moons. Such studies will not only improve our understanding of these enigmatic planets, but will also shed light on the formation and evolution of the solar system. Among the myriad scientific instruments and revolutionary technologies aboard the Voyager spacecraft is a message not for us, but for the unknown, for the future, or perhaps for other space dwellers. That message is the Golden Record, a 12-inch gold-plated copper disc on which are recorded sounds, images, music, and greetings from Earth. The Gold Record serves as a time capsule, a snapshot of humanity and our planet at the end of the 20th century. Its contents have been carefully selected to show the diversity of life and culture on Earth, from the sounds of nature, such as birdsong and the sound of the ocean, to music from different cultures and eras, including Bach, Beethoven, and traditional music from around the world. Decisions about the content of the Golden Record were guided by the desire to present a comprehensive picture of Earth and humanity. The team, led by Carl Sagan, put a lot of thought into including content that would not only convey the complexity and beauty of life on Earth, but also reveal fundamental scientific concepts, such as the structure of DNA and the location of our planet in the solar system. The cover of the Golden Record is decorated with symbolic instructions, the universal language of science and mathematics, designed to tell potential aliens how to decipher the disk. These symbols explain the origins of the record and provide instructions on how to play the audio content, ensuring that the message is understood throughout the space, transcending language and cultural barriers. The record is a testament to humanity's hope and desire for contact, communication, and connection, not only with our future generations, but perhaps with other beings who will one day find this bottle tossed into the cosmic ocean, carrying a message of a small, distant world full of life and dreams. As Voyager 1 and Voyager 2 continue their silent odyssey into the depths of interstellar space, the task of keeping in touch with these distant explorers is becoming increasingly difficult. Billions of miles from Earth, the faint signals transmitted by the spacecraft take more than 22 hours to cross the cosmic expanse and come like whispers from the void. The Deep Space Network, an array of giant radio antennas scattered around the globe, serves as the ears of the Earth, listening intently to the faint signals of spacecraft. As the spacecraft travel farther into space, the ingenuity and foresight of the engineers who designed and built these probes becomes increasingly evident. The longevity and success of the missions can be attributed to an amazing feat of engineering. Designed to last only 5 years, the spacecraft have exceeded their expected lifespan many times over, thanks to redundant systems, robust construction, and the use of radioisotope thermoelectric generators, or RTGs, for power generation. These RTGs convert the heat generated by the decay of plutonium-238 into electricity that fuels the spacecraft's instruments and communication systems. As RTG power decreases, mission controllers are faced with making difficult decisions about which instruments should continue to operate. This careful management of dwindling resources ensures that the most important science instruments remain operational for as long as possible, continuing to collect invaluable data at the frontiers of space. Looking ahead, we expect the Voyagers to continue their silent journey long after their last instruments have fallen silent. Driven by the momentum of their initial launch and gravitational support, they'll drift as emissaries of Earth, perhaps for billions of years. The idea that these spacecraft may one day be the only remaining evidence of humanity's existence, taking the golden records into the cosmic ocean, has its poetic note. The final frontier for Voyager is marked not by a physical boundary, but by our ability to communicate across vast cosmic distances. But even as spacecraft fade into silence, their legacy lives on, a testament to human curiosity and the unquenchable desire to explore the unknown. Humanity stands on the threshold of a new era, an era defined not only by exploration, but also by the bold dream of colonization. For decades, our gaze has been fixed on the familiar, the Moon, our celestial neighbor, and Mars, the red beacon in our night sky. These worlds, once the subject of science fiction, now beckon us with the promise of new frontiers. But beyond these well-trodden paths lies a world shrouded in mystery, a world that's changing our understanding of what it means to be a moon. This is Titan, Saturn's largest satellite. Titan is a world covered with a dense atmosphere, which is rare for a moon. It's a place where rivers and lakes flow not with water, but with liquid methane and ethane. Here, the sky is raining gasoline. And the cold is beyond anything that can be experienced on Earth. Yet, in this alien landscape lurks the potential for something extraordinary. Could Titan, a world so unlike our own, hold the key to our future in space? Could this distant moon hold the secrets to not only surviving, but thriving beyond our home planet?
It's one small step for man, one giant leap for mankind.
As we turn the pages of our history of space exploration, the Moon and Mars become beacons of human ambition. The Moon, our nearest celestial neighbor, has always been a constant companion in our night sky, a symbol of our desire to leave the confines of the planet. Mars, in turn, with its striking resemblance to Earth, fuels our dreams of finding a new home in space. Nevertheless, the Moon, despite its proximity, presents serious problems. Its surface is a barren wasteland, devoid of atmosphere and offering no protection from the harshness of space. The lunar environment is a vacuum, exposing astronauts to extreme temperatures and cosmic radiation. No atmosphere means no air to breathe, no wind to carry sound, and no sky to protect against the relentless barrage of solar and cosmic rays. Mars, though more Earth-like, is not without its own problems. Its thin atmosphere, consisting mostly of carbon dioxide, offers little protection from solar and cosmic radiation. The Martian environment is harsh and merciless, and temperatures at the poles can drop to minus 257 degrees Fahrenheit. The lack of a global magnetic field exposes the surface to the full force of the solar wind and cosmic rays. In contrast, Titan, Saturn's largest satellite, presents a very different environment. Shrouded in a dense atmosphere, Titan offers a natural barrier against the dangers of cosmic radiation. This atmosphere, richer in nitrogen than even the Earth's atmosphere, is the key to protecting future colonists from cosmic rays that mercilessly bombard less protected worlds such as the Moon and Mars. Titan's atmosphere isn't just a shield, it's a gateway to opportunity. Unlike the Moon and Mars, the air pressure on Titan's surface is 1.5 times higher than on Earth, creating a surprisingly familiar pressure environment for human explorers. This dense atmosphere opens up new possibilities for exploration and colonization, possibilities that are beyond the reach of our more trivial space goals. As we rethink our goals for space colonization, Titan becomes a compelling alternative, a world in which the atmospheric and radiation problems that limit our ambitions on the Moon and Mars become its strengths. Titan invites us to envision a future in which humanity can thrive under the protective embrace of an alien sky, a future in which the mysteries of this distant moon become stepping stones to our expansion into space. As we mentioned earlier, Titan, a moon of many mysteries, orbits around Saturn. Discovered in 1655 by Dutch astronomer Christian Huygens, Titan has captivated the imagination of scientists and dreamers ever since. This world is both similar to and in stark contrast to our Earth. Titan's environment is unlike anything else we've encountered in our solar system. It's the only known moon with a dense atmosphere, and the second largest moon in our solar system after Ganymede, a satellite of Jupiter. But it's not just the size that makes Titan stand out, it's the rich composition of its atmosphere and surface that really sets it apart. This moon is surrounded by a thick, nitrogen-rich atmosphere, similar in composition to Earth's, but far denser and more extensive. It's permeated with organic molecules, creating a kind of hazy orange glow that obscures the surface of the satellite from view. It's this nitrogen-dominated atmosphere that provides protection from solar radiation. which contrasts sharply with the barren sky of the Moon, and Mars. Beneath this alien sky lies a landscape at once familiar and utterly alien. Titan's surface is formed by rivers and lakes, but they're not bodies of water as we know them. Instead, they're filled with liquid methane and ethane, flowing through channels carved into the Moon's icy crust. These hydrocarbon seas are a true marvel, a testament to the diversity of the universe's chemistry. The presence of these surface fluids is a key characteristic that distinguishes Titan from other celestial bodies. On Earth, the water cycle shapes climate and geography. On Titan, a similar cycle occurs, but the role of water is played by methane and ethane. This hydrocarbon cycle, with methane rain and ethane lakes, creates a dynamic environment that may provide clues to understanding the complexity of planetary atmospheres. So, by breaking the limits of our standard perception, we're slowly uncovering exactly what makes a planet or moon habitable. Its nitrogen-rich atmosphere and surface fluids open the door to new possibilities. Let's find out what they are. So the Moon's nitrogen-rich atmosphere provides a natural barrier against cosmic radiation, a major challenge for space colonization. Why do we pay so much attention to solar radiation? Well, the answer is simple, yet profoundly important. Solar radiation is a ruthless destroyer of living cells. It doesn't just affect microscopic life forms, it directly affects us as human beings. Unshielded exposure to solar radiation can cause severe cellular damage, destroying the very fabric of our biological existence. In space, spreading uncontrollably, this radiation poses one of the greatest threats to the survival and health of astronauts. On Earth, it's the atmosphere and magnetic field that protect us. On Titan, it's the dense nitrogen atmosphere that provides vital protection, making it a safer haven for future human colonists than the barren landscapes of the Moon or Mars. Beneath this protective dome is a world of liquid methane and these hydrocarbon lakes and rivers stand in stark contrast to the bodies of water we know on Earth, yet they offer intriguing possibilities. Imagine a world where boats sail on methane seas, where the familiar concept of the liquid cycle takes on a whole new form. The presence of these surface fluids is not just a curiosity, it's a resource. Methane and ethane have the potential to be used as fuel, providing energy for future colonies. This abundance of hydrocarbons makes Titan an attractive target for colonization, offering a solution to one of the biggest problems of space habitation: sustainable energy sources. But Titan's gifts don't end there. Beneath its icy surface lies another treasure: water ice. The very water so essential to human life is abundant on the satellite, trapped in its frozen crust. The presence of water ice, along with hydrocarbons, makes this moon a repository of vital resources, setting the stage for a self-sustaining human presence away from Earth. Titan, a world of incalculable potential, also presents enormous challenges. Severe cold, during which temperatures drop to minus 356 degrees Fahrenheit, creates an environment unsuitable for human life as we know it. In turn, methane rain, a phenomenon unique to this moon, adds another layer of complexity to the survival equation. To overcome these challenges, we must turn to the pinnacle of human ingenuity and technology. Colonizing Titan will require not just adaptation, but a complete rethinking of human habitation in extreme conditions. Imagine dwellings designed to withstand low temperatures, insulated with materials yet to be invented, and harnessing the power of Titan's own resources to provide warmth and comfort. These habitats could be equipped with systems to convert atmospheric methane into heat, turning the problem itself into a resource for solving it. But survival is more than just keeping warm. Methane rain, while an obstacle, could turn into an advantage. Advanced collection and filtration systems could recycle methane not only as an energy source, but also as a raw material for essential commodities. Now, let's imagine a human colony on Titan. Imagine domed cities, their architecture a blend of science and art, designed to harmonize with Titan's unique environment. These structures, resistant to cold and methane rains, would be interconnected, forming a network, demonstrating human resilience in the face of alien conditions. Inside these domes, life thrives. Hydroponic gardens provide food, recycling systems conserve resources, and public areas foster a sense of community. It's a place where humanity has not just survived, but flourished, adapting decisively to Titan's challenges. Colonizing Titan is not just a distant dream, it's a future that beckons us to take up the challenge. With each technological breakthrough, with each bold leap of imagination, we come closer to making this alien world a new home for humanity. Watching the thriving human colony on Titan, it becomes clear that this moon is more than just a new home for humanity. It's a center of economic and scientific opportunity. The unique environment and abundant resources offer unprecedented prospects for both. The economic benefits of colonizing Titan are rooted in its vast hydrocarbon reserves. Key components of Titan's lakes and atmosphere are not only potential sources of energy, but also valuable raw materials for chemical synthesis. The ability to harness these resources could turn Titan into an economic center, meeting both the colony's needs and potentially supplying materials for interplanetary trade. Scientifically, Titan is a gold mine. Its complex atmosphere and surface chemistry offer unique research opportunities that offer insights into organic chemistry and astrobiology. Studying Titan's methane cycle and its prebiotic chemistry could unlock the secrets of the origin of life, not only on Earth, but potentially throughout the cosmos. Moreover, Titan's position in the solar system and its resources make it an ideal launching pad for future space exploration. Its low gravity and abundant fuel reserves could make it easier to launch spacecraft to distant destinations, making Titan a strategic outpost for exploring the outer solar system and beyond. However, with these opportunities come important ethical considerations. As we embark on the colonization of Titan, we must reflect on our responsibilities in interacting with the new world. Conservation of Titan's environment, respect for its unique characteristics, and thoughtful stewardship are paramount. We must approach Titan not as conquerors, but as custodians. How we relate to this world in the future will reflect our values and our ability to balance progress and responsibility. As we conclude our journey, let's reflect on the key points. A moon once shrouded in mystery has turned out to be a world full of potential. We explored the protective properties of Titan's nitrogen-rich atmosphere, a natural shield against the dangers of cosmic radiation. We traveled through alien landscapes where rivers and lakes of methane and ethane cut through icy terrain, offering resources that could secure our future in space. Our journey also took us to the potential of a vibrant human habitat, where ingenuity and resilience have turned challenges into opportunities. We saw how Titan's economy, driven by its abundant resources, can be a cornerstone of our interplanetary endeavors. As we ponder the future of humanity on Titan, we're reminded that colonization is not just about achieving technological perfection. It's a journey that forces us to grow, learn, and respect the universe we live in. So we leave you with a great question. What does this step mean for the future of humanity? How will our efforts on this distant moon affect our destiny in the vast, uncharted expanse of space? In a universe dominated by ancient massive structures, there are places where something unexpected happens that defies the cosmic norm. New galaxies emerge. These rare formations are changing our idea of how the cosmos should behave. While the Milky Way and Andromeda seem to have entered their mature phase, somewhere out there in the far corners of space, young galaxies are still being born, glowing with the energy of new star formation. But why do these exceptions exist? What forces allow them to thrive when the rest of the universe has slowed down? By exploring these distant regions, we learn about the forces that lead to the formation of such grand structures, the role of dark matter in all of this, and the mysterious processes that allow some galaxies to defy the passage of time. The discovery and classification of galaxies was a milestone in our understanding of the universe. In the early 20th century, observations by Edwin Hubble showed that the nebulae observed in telescopes were not just gas clouds inside our galaxy, but entire galaxies, each containing billions of stars. This discovery expanded our understanding of the cosmos beyond the Milky Way, revealing a universe teeming with distant galaxies. Soon, galaxies were categorized by their shape: spiral, elliptical, and irregular. These classifications helped astronomers create a more organized view of the cosmos, which led to further study of the origin and evolution of these huge structures. However, as our observations deepened, a surprising pattern emerged. The vast majority of galaxies observed were ancient, dating back almost to the very beginning of the universe. This discovery was unexpected. When the first detailed studies of galaxies were conducted, scientists expected to find a range of galaxy ages, including recently formed galaxies. However, instead of a universe full of young galaxies still in the formation stage, they found that most galaxies had already reached maturity. These findings challenged existing theories of cosmic evolution at the time, raising questions about how and when galaxies formed. At first, the scientific community was stunned. The rarity of young galaxies seemed to contradict the ongoing process of star formation that's still observed in the universe today. This paradox, the presence of ongoing star formation in predominantly ancient galaxies, posed a serious question to our understanding of galaxy formation and evolution. As astronomers delved deeper into this mystery, they began to realize that the formation of galaxies may not be as simple as previously thought. The processes that govern the early universe, such as the distribution of dark matter and the influence of cosmic structures, seem to have played a more important role in shaping its landscape than first thought. These factors likely contributed to the rapid formation of galaxies shortly after the Big Bang, leading to a shortage of newly formed ones in the modern era. Determining the age of galaxies is a complex task that relies on a variety of methods, most of which focus on the age of the stars within them. For example, astronomers have used several methods to estimate the age of the stellar population of the Milky Way and Andromeda. One of the main methods involves studying the distribution of stars in the Hertzsprung-Russell diagram, or HR diagram, which shows the dependence of the luminosity of stars on their temperature. In particular, astronomers focus on the turning point of the main sequence, the stage at which stars begin to leave the main sequence and turn into red giants. This point is very sensitive to age. The position of the pivot point on the HR diagram can give an accurate estimate of the age of the stellar population. Another important method is the study of globular clusters, dense groups of ancient stars orbiting around the outskirts of galaxies. The age of these clusters is also determined by the rotation points of the main sequence of their stars. And since globular clusters are among the oldest objects in the galaxy, they provide crucial clues about their formation history. For example, the oldest globular clusters in the Milky Way are about 13 billion years old, indicating that the Milky Way itself formed shortly after the Big Bang. In addition to studying star clusters, astronomers also use spectral analysis. By analyzing light spectra, particularly absorption lines, they can determine the relative proportions of different types of stars. Older galaxies are dominated by red, cooler stars, while younger galaxies have more blue, hotter stars. The discovery that many galaxies, including the Milky Way, formed nearly 13.8 billion years ago, shortly after the Big Bang, was a significant breakthrough in cosmology. The rapid collapse of clouds of primordial gas under the influence of dark matter probably played a crucial role in these early formations. This process laid the foundation for the cosmic structures we see today. So the formation of galaxies in the early universe is a story deeply intertwined with the mysterious and influential presence of dark matter. In the chaotic period after the Big Bang, the universe was a hot, dense soup of particles in which matter and radiation were tightly bound together. As the universe expanded and cooled, gravity began to pull matter together into the first structures, tiny clumps of matter, known as proto-galaxies. According to scientists, dark matter played a key role in this process. Unlike ordinary matter, which interacts through the electromagnetic forces and radiation, dark matter interacts mainly through gravity. Because of this, dark matter began to stick together earlier than ordinary matter, forming the basis on which the first galaxies eventually formed. These dense regions of dark matter, often called dark matter halos, provided the gravitational wells needed to pull in gas and dust, leading to the formation of the first stars and eventually the first galaxies. These early galaxies were relatively small and simple compared to the huge and complex galaxies we see today. They were often irregularly shaped and lacking a distinct structure, such as that of the Milky Way. But over time, driven by the gravitational pull of dark matter, these proto-galaxies began to merge and interact. As proto-galaxies merged, they grew in size and complexity, forming more massive structures that eventually evolved into the spirals, ellipticals, and irregular shapes that populate the modern universe. This period of intense formation and merger is often referred to as cosmic noon, a time of active star formation and growth through mergers at a much higher rate than we observe in the modern universe. So why are newly formed galaxies such a rarity in the modern universe? One of the key factors contributing to this phenomenon was the very process of galaxy mergers. In the early universe, when galaxies were smaller and more numerous, there were frequent interactions and collisions between them. However, as the universe expanded and matured, such collisions became less frequent, resulting in fewer new galaxies. Another factor is the changing influence of dark matter halos. In the early universe, halos were smaller and more concentrated, favoring the collapse of gas and the formation of new stars and galaxies. As the universe expanded, it became larger and more diffuse, making it harder for the gas to cool and condense into new formations. The large-scale structure of the universe, often referred to as the cosmic web, also plays a notable role in this process. Galaxies are not randomly distributed, but are arranged along huge threads of dark matter that stretch across the cosmos, connecting galaxy clusters. Along these threads, gas flows into them, fueling the star formation process. However, in the present epoch, most of the gas has already been consumed or trapped in larger and more stable structures, which also leads to a decrease in the rate of new formation. However, despite all that we've just said, there are rare cases that violate this trend. One such example is the dwarf irregular galaxy known as ISWICKY 18. Located about 45 million light-years away, this galaxy is notable for having a relatively recent burst of star formation. Unlike most, ISWICKY 18 began its first major burst of star formation only about 500 million years ago, well after the period when most galaxies in the universe were fully formed. The slow evolution of ISWICKY 18 represents an intriguing case in the study of galaxy formation. Its star-forming regions are characterized by intense ultraviolet emission and stellar winds from young massive stars. The presence of these young stars, combined with the overall low metallicity, suggests that IceWiki 18 did not undergo the same evolutionary processes as most other galaxies. This late bloom may provide clues to the conditions favoring delayed star formation and raise the question of the role of environmental factors, such as nearby galaxy interactions in triggering or suppressing star formation. Another notable case is a galaxy with a rather unwieldy name of HSC J1631 plus 4426, discovered through observations with a Subaru telescope. Located 430 million light-years away, this specimen is not only young, but also holds the record for the lowest observed oxygen content. The low oxygen content indicates that the galaxy is in the very early stages of its formation and has only recently begun to convert primordial hydrogen and helium into heavier elements through stellar nucleosynthesis. The galaxy's small size, about 0.8 million solar masses, comparable to a star cluster in our Milky Way, further emphasizes its youth. The fact that such a young and small specimen exists so late in the history of the universe is surprising, given that in the early universe, the conditions for galaxy formation were much more favorable. And given that the expansion of the universe continues to accelerate, making conditions for the formation of new galaxies more and more impossible, such findings become quite extraordinary. At the same time, star formation is a continuous process that continues even in ancient galaxies. And star clusters such as the Pleiades provide clear evidence of this ongoing activity. The Pleiades, often referred to as the Seven Sisters, is a young open star cluster located just 448 light-years from Earth. Despite the age of the Milky Way galaxy being over 13 billion years old, the Pleiades cluster is a relative newcomer, having formed only about 100 million years ago. This indicates that even in such a mature galaxy as ours, there are still regions of active star formation. The formation of star clusters like the Pleiades usually occurs in regions of galaxies where there's a high concentration of gas and dust. These molecular clouds collapse under their gravity, giving birth to new stars. In the case of the Pleiades, the stars of the cluster are still relatively young and hot, and they emit bright blue light, making the cluster visible to the naked eye. Such star clusters are not unique to our galaxy. In neighboring galaxies, such as the Large Magellanic Cloud, abbreviated LMC, star formation is also ongoing. The LMC, a companion galaxy to the Milky Way, contains the oldest known stars as well as regions where new ones are still forming. One such ancient star, LMC 119, that was only discovered this year, is believed by scientists to be about 13 billion years old. This discovery highlights the remarkable longevity of some stars and suggests the conditions for star formation are still not fully understood by us. These star-forming regions are not just remnants of the past, but a critical factor in the future evolution of galaxies. As new stars form, they contribute to ongoing dynamical processes in their host galaxies, affecting everything from the formation of planetary systems to the distribution of elements necessary for life. While star formation continues in some regions of galaxies, like the Milky Way, a significant factor affecting the overall evolution of these galaxies is the presence of the previously mentioned dark matter halos. These halos extend far beyond the visible edges of galaxies and play a crucial role in their formation and structure. As we know, dark matter has a significant gravitational influence on galaxies. This influence is most evident in the way galaxies rotate. Observations have shown that the outer regions of spiral galaxies, including the Milky Way, rotate much faster than would be expected with only visible matter. This discrepancy suggests the presence of a massive invisible component forming a spherical halo around the galaxy. The dark matter halo not only stabilizes galaxies, but also affects their ability to form new stars, and, consequently, new galaxies. In the early universe, dark matter halos provided the gravitational wells necessary for the collapse of gas and the formation of the first galaxies. Over time, however, these halos grew in size and became more diffuse, preventing the formation of new galaxies. The expanding halos, with their enormous gravitational influence, can prevent the gas from cooling and condensing into new stars, effectively suppressing the birth of new galaxies in the current epoch. These dynamics create a delicate balance in the cosmos, where dark matter both promotes and inhibits the growth of cosmic structures. According to scientists, the presence of such halos is one of the key reasons why we see fewer new galaxies forming today compared to the early universe, marking a significant shift in cosmic evolution. Understanding the formation and evolution of galaxies remains one of the most serious challenges of cosmology. Despite significant progress, debates about the fundamental processes that shape the universe are still ongoing. One of the key debates concerns the formation of structures in the cosmos, whether it occurs according to the top-down or bottom-up approach. According to the top-down model, large cosmic structures form first, and then they break up into smaller galaxies and clusters. According to this model, the largest galaxies and galaxy clusters appeared at the very beginning of the universe's history, and smaller structures were formed as these large structures decayed. In contrast, the bottom-up model suggests that small structures formed first, and tiny proto-galaxies and star clusters eventually merged to form larger galaxies and clusters. This theory is consistent with the observed hierarchical nature of the universe, where small objects merge into more complex and massive systems over billions of years. Although these models provide a foundation for understanding galaxy formation, recent observations have revealed complexities that challenge both theories. For example, the discovery of ancient massive galaxies in the early universe suggests a more subtle interaction between these processes, perhaps indicating that the true nature of cosmic evolution is a combination of both scenarios. Nevertheless, the search for and understanding of new galaxies continues to drive astronomical research. JWST has already opened new windows into the distant universe, allowing astronomers to peer into an era when galaxies were just forming. One of the most intriguing questions is whether new galaxies are still forming today. While the early universe was fertile ground for galaxies to form, today's cosmic landscape presents a different picture. As the universe expands and dark energy accelerates this expansion, conditions suitable for galaxy formation become increasingly rare. Future astronomical missions are poised to push the boundaries of our knowledge even further. Instruments such as the Vera C. Rubin Observatory and the European Space Agency's Euclid mission will shortly carry out deep space surveys that are likely to reveal new galaxies that have eluded previous observations. These missions are aimed not only at discovering new galaxies, but also at unlocking the mysteries of dark matter, dark energy, and the overarching structure of the universe. History of the universe is far from complete. As we continue to explore the cosmos, discoveries change our understanding and raise new questions. Each glimpse into the distant past brings us closer to unraveling the mysteries of the universe's formation and fate. Stay tuned for more discoveries to come. What lies beyond the observable universe? As we gaze into the celestial tapestry, our understanding stretches from the familiar glow of our solar system to the enigmatic dark spaces that challenge every truth we hold dear. From the rudimentary lenses of Galileo, which first charted the moons of Jupiter, to the intricate orbits of modern space telescopes capturing distant galaxies, our tools for probing the cosmos have evolved dramatically. Yet each discovery peels back only a layer of more profound mysteries ahead. The intriguing presence of dark matter and dark energy suggests that much of the universe is shaped by substances and invisible forces, dictating the speed at which galaxies rotate and the universe expands. But could there be more than our universe? The theory of the multiverse proposes a spectrum of possibilities where different laws of physics may apply. Each discovery, from black holes bending the fabric of space-time to gravitational waves echoing through the cosmos, is a puzzle in understanding the broader cosmic picture. These cosmic phenomena challenge our perceptions and invite us to contemplate the more profound mysteries that define our universe and possibly others. Are we ready to redefine our understanding of the cosmos and accept the boundless realms of the multiverse? This narrative challenges our perceptions and invites us to explore the profound implications of what lies beyond the observable universe. As humankind has plumbed the depths of the universe, it's begun to encounter phenomena that our traditional understanding of physics could not describe. Among them are dark matter and dark energy, components of the cosmos that remain invisible to our telescopes, but profoundly affect the structure and fate of the universe. The mystery of dark matter first arose from the study of the rotation curves of galaxies. According to Newtonian mechanics, stars at the galaxy's outer edges should rotate slower than in the center, like the planets in our solar system. However, observations have shown that this is not the case. Instead, the rotation rate of stars and galaxies remains constant, suggesting that there is an invisible mass exerting an additional gravitational force. This matter, detectable only through its gravitational influence, forms the entire skeleton of the universe. Turning our gaze from the hidden mass inside galaxies, we encountered an even more elusive component: dark energy. This mysterious force drives the universe's accelerating expansion, a phenomenon first detected by the strange behavior of distant supernovae. Instead of slowing down, as one might expect from the gravitational pull of the entire universe's mass, its expansion is accelerating. Among these expansive forces, black holes anchor the cosmic drama. Born from the collapsing cores of massive stars, these gravitational giants warp space-time to the point where even light cannot escape their grip. The first direct image of a black hole's event horizon revealed a universe stranger and more fantastic than we could have imagined. And rather than providing new answers, it only added questions to those already existing. However, the interaction of these cosmic giants is not silent. When black holes merge, they send gravitational waves throughout the universe, rips in space-time that we've only recently begun to detect. Observatories like LIGO and Virgo are capturing these waves, giving us new insights into some of the most violent events in the universe. Gravitational waves have opened a new channel through which we can explore the cosmos, complementing the electromagnetic spectrum that's been our primary window into the universe. By analyzing these waves, scientists can unlock the secrets of black hole masses, rotations, and merger details, enriching our understanding of the fundamental physics that governs the most extreme objects in the universe. But this is only part of humanity's quest to understand the cosmos's cruel mechanisms and find potential cradles for life throughout the universe. The search for exoplanets and the search for extraterrestrial intelligence represent two journeys into the unknown, guided by our deep curiosity about the cosmos. The discovery of myriad worlds orbiting stars within our galaxy has opened a new chapter in our understanding of the universe, expanding our horizons beyond our solar system to include many planets with conditions as diverse as those on Earth. Each discovery, from the sultry surfaces of hot Jupiters to the potentially habitable conditions on super-Earths, becomes the basis for a broader story about our place in the universe. With its unprecedented observational capabilities, the James Webb Space Telescope allows us to peer into the atmospheres of these distant worlds, analyze their composition, and look for signs of life. This bridge to the stars is not just about discovering new planets. It's about understanding the conditions that can support life, a question that naturally extends to the search for signals from civilizations beyond our planet. Meanwhile, an initiative known as the Search for Extraterrestrial Intelligence, or SETI, has continued for decades to explore the silent expanse of space, listening for faint whispers of civilizations that may exist in these distant worlds. Use of technologies covering a vast electromagnetic spectrum, SETI's efforts underscore the enormity of our search and the tantalizing possibility that we are not alone. At the heart of SETI's theoretical foundation is the Drake equation. Formulated by astronomer Frank Drake in 1961, the equation offers a way to estimate the number of active, friendly, extraterrestrial civilizations in the Milky Way galaxy. The equation considers factors such as the star formation rate, the fraction of stars with planetary systems, the number of planets on which ecosystems can develop, and the likelihood of intelligent life. The equation highlights the vast number of unknowns in this search, from the fraction of habitable planets with life to technological civilizations' longevity. Nevertheless, searching for the potential for life in space is only the beginning. The deeper we delve into the mysteries of the cosmos, the more our knowledge expands, and the more questions arise. The constant change in our understanding of the cosmos lays the groundwork for considering even more possibilities. The enigmatic phenomena discovered in the course of these investigations, the invisible scaffolding of dark matter, and the pressure of dark energy on the expansion of the universe, provide the basis for considering the multiverse not as science fiction, but as a plausible structure that can explain mysteries that remain beyond our current scientific reach. Our current search, limited to the observable universe and based on our understanding of life on Earth, can only scratch the surface of what's truly possible. Multiverse theory opens up an even more comprehensive range of possibilities, reaching beyond our observable universe into realms where the fundamental laws of physics may be radically different. The Drake equation, which is the basis for our search for extraterrestrial intelligence by estimating the number of friendly civilizations in our galaxy, operates within the physical laws of our universe. However, if we embrace the multiverse theory, the equation may be just one of countless ways to understand the potential for life in a more extensive and diverse multiverse landscape. In general, the multiverse concept pushes the boundaries of our cosmic understanding into new, uncharted territories. It suggests that our universe, as vast and complex as it is, may be only one of a vast number, perhaps an infinite number, of universes existing parallel to our own. The seeds of the multiverse theory are in quantum mechanics and cosmology. With its probabilistic nature, quantum mechanics introduces the idea of parallel outcomes arising from the same quantum events. If we apply this principle to cosmological scales, we can assume that in the universe, each possibility is realized in its own separate cosmos. Cosmic inflation, a theory describing the exponential expansion of the early universe, provides another basis for a multiverse. Inflation suggests that bubbles of space may have formed, each expanding into its universe with a larger multiverse. These bubbles may have different properties and physical laws dictated by the nature of the inflationary field in each region. Most conceptions of the multiverse are not monolithic. They include several models, each with its implications for our understanding of reality. Bubble universes emerging from the theory of cosmic inflation. Bubble universes are distinct regions within a large space, each having undergone its inflationary expansion. These universes can radically differ from our own, with different physical constants and laws. Quantum multiverses, based on quantum mechanics. This interpretation asserts that each quantum decision point generates a new parallel universe. Every conceivable outcome of any event generates its universe, resulting in an almost unimaginable variety of parallel histories and futures. Mathematical universes, This model assumes the existence of all mathematically possible universes. If physical laws, as we understand them, are merely mathematical structures, then all structures that can be described mathematically exist as tangibly as our universe. For example, let's look at the type of multiverse classified by astrophysicist and cosmologist Max Tegmark. Level 1, the infinite universe. At the first level of the Tegmark model, the universe extends infinitely beyond the observed cosmos. At this level, it's assumed that our observable universe, 92 billion light-years in diameter, is just an infinitesimal particle in an increasingly vast cosmic landscape. Every structure, event, and variation is infinitely repeatable in space, suggesting that our duplicates exist somewhere in similar conditions, if not identical. Level 2, the post-inflationary multiverse. The second level of Max Tegmark's multiverse model explores the realm where individual universes arise from their own unique Big Bang events. This classification is rooted in the concept of chaotic inflation, which assumes the existence of a cosmos in which our universe is just one of countless others, generated by inflationary bubbles. Chaotic inflation assumes that the rapid expansion of the universe, which we think of as the Big Bang, is not a single event, but a common phenomenon throughout cosmic history. In this model, inflation never stops completely. It stops only locally, like bubbles forming and separating in boiling water. Each bubble becomes a new universe with potentially different physical constants. In these individual universes, the fundamental constants and even the laws of physics can change from bubble to bubble. These differences can lead to universes that are radically different from our own. For example, gravity may be stronger in one universe, affecting the formation and evolution of stars and galaxies. In another, different levels of electromagnetic forces may change the chemistry of life, of course, if life is even possible in it. To understand the implications of changing these constants, imagine throwing a ball in a universe where gravity is 3 times stronger than it is here. The ball would not fly as far or as high, fundamentally changing games like basketball or soccer. If you extend this analogy to celestial mechanics, you can imagine that planets could orbit much closer to their stars, and stars could be smaller and burn up faster. If physical constants can vary so widely, then the conditions that led to the emergence of life on Earth are just one possibility of a vast cosmic lottery. Each universe may be a unique experiment to explore the possibilities of physical reality. Although second-level multiverses differ fundamentally in their constants, they share a common link with their first-level multiverses, where all the laws of physics are constant, but the initial constants vary. This multi-level structure of the multiverse not only expands our understanding of what's possible, but also provides a basis for understanding the incredible variety of conditions under which universes can form. Level 3, the many worlds interpretation of quantum mechanics. Perhaps the most disconcerting of Tegmark's levels, the third level, introduces the concept of quantum mechanics into the multiverse theory. According to the interpretation of multiple worlds, every possible outcome of every event defines or gives rise to a new world or universe. This level assumes infinite timelines and possibilities where each conceivable scenario takes place in its own universe. Imagine a simple everyday decision, such as turning left or right on your way to work. In the many worlds interpretation, each choice results in a branching universe. One version of you turns left, while another version turns right in a parallel universe. These universes exist simultaneously, but do not interact with each other, and each follows its path of reality based on that single quantum decision. Another example is the flip of a coin. In our everyday experience, the coin falls either heads or tails. However, in the context of the many worlds interpretation, at the moment of the coin flip, the universe is split into 2, one where the coin falls heads and one where it falls tails. Each outcome exists in its separate universe. And the consequences of this simple event spread outward, affecting further events in each respective universe. However, this interpretation goes beyond human-scale events and encompasses all quantum events in the universe. For example, the same decay of a radioactive atom, a fundamentally random process at the quantum level, would cause the universe to split into one in which the atom decayed and one in which it did not. Each of these universes would continue to evolve independently, accumulating its unique history. The fascinating aspect of this level of the multiverse lies not only in its scientific implications, but also in the way it reflects the complexity of human choices and the inherent unpredictability of life. Just as we can ponder what-if scenarios regarding our past decisions, the interpretation of many worlds realizes these alternatives in countless parallel universes. Level 4, Ultimate Ensemble. The fourth level of Max Tegard's multiverse classification represents the most radical and profound conception of all possible universes. In this model, known as the mathematical universe hypothesis, reality is viewed as a landscape of mathematical structures. Each structure defines a separate universe, distinguished not only by physical constants or laws, but also by potentially entire mathematical structures. According to the hypothesis of mathematical universes, our physical world is not just described by mathematics, it is mathematics. This means every conceivable mathematical structure exists as a physical reality somewhere in a multiverse. These universes may function based on entirely different mathematical rules than the ones we know and understand. To illustrate this profound concept, let's take a simple object like an orange. Imagine holding an orange in your hand. It's familiar and tangible. But this orange is a set of mathematical properties at its core. The shape of the orange, the ideal sphere, is not just a physical form, but a geometric expression that describes contours and volume, defining how the orange exists in space. Now, think about the orange color that we see. This bright hue is not just a random feature. It results from light interacting with molecules on the orange's surface that absorb and reflect light at specific wavelengths. Because the science of light, optics, is deeply mathematical, it relies on equations that describe how light behaves when it encounters an object. Even the taste of an orange, the combination of sweetness and acidity, is driven by chemical reactions that can be quantified and predicted with mathematical precision. The concentrations of sugars and acids are subject to chemical laws, essentially mathematical relationships that determine how substances interact. Every aspect of an orange, from its growth to the sensations it evokes when we eat it, can be described using math. In this way, this simple fruit becomes a small, tangible proof of a much larger truth. Our entire universe, from the smallest atom to the largest galaxy, can be part of a grand mathematical structure. If we accept that every mathematical structure corresponds to a physical universe, the implications for science and philosophy are enormous. It implies that any universe that a consistent set of mathematical rules can describe exists as surely as our own. It implies that universes with radically different properties that defy our physical intuition are just as real as our own. Consider a universe in which the dimensions of space and time are not 4, as in our visible universe, but 5, 10, or even more. The behavior of particles and forces in such a universe could be radically different, changing the process of matter formation and evolution. Or imagine a universe governed by a different type of geometry, where the shortest path between 2 points is not a straight line, but some other curve which radically changes the structure of the universe and the life it can support. Level 4 is connected to the other levels of the multiverse, providing the ultimate framework. While levels 1 to 3 deal with the universes that differ in initial conditions, physical constants, or quantum results, Level 4 encompasses all possible mathematical realities. It offers a cosmos where the boundaries of possibility are limited only by the limits of the mathematical imagination. The implications of the multiverse theory go beyond physics and into philosophy, forcing us to think about the most fundamental concepts of reality, causality, and existence. If the multiverse is real, it means that with all its complexity and beauty, our universe is just one of countless others, each with its own history, laws, and perhaps even life forms. In the scientific realm, the multiverse theory raises profound questions about the nature of scientific inquiry and evidence. Since other universes in the multiverse are, by definition, beyond our observation, the theory walks a fine line between physics and metaphysics, forcing us to reflect on views of the principles of empirical science.
That's one small step for man, one giant leap for man.
As we ponder the vastness of the universe and the possibility of countless worlds in the multiverse, our quest for space exploration continues to propel us forward. The next chapter in human space exploration is being written now, with ambitious programs and missions that aim to expand our presence beyond Earth, back to the Moon, onward toward Mars, and eventually beyond our solar system. In conjunction with international and commercial partners, NASA's Artemis program marks a major milestone in our efforts to explore the Moon. Named after Apollo's twin sister, the Artemis program aims to return humans to the Moon by the mid-2020s, with the lofty goal of a sustained human presence there by decade's end. Unlike the Apollo missions, which were short-term visits, Artemis envisions a long-term presence of humans and robots on the Moon, utilizing its resources and using it as a testing ground for technologies needed for deeper space exploration. The Artemis architecture includes Gateway, an orbital lunar outpost that will support long-term human missions to the Moon and serve as a transfer point for missions to Mars and beyond. Gateway will facilitate scientific research, provide a platform for testing new technologies, and usher in a new era of the international cooperation in space. In turn, the red planet Mars has long captured our imagination as the next frontier for human exploration. Based on decades of robotic exploration, plans for manned missions to Mars are taking shape to send astronauts to Mars in the 2030s. These missions will require improvements in life support, propulsion, and habitat technologies, and a better understanding of the psychological and physiological effects of long-duration space travel. Human missions to Mars will aim not only to answer fundamental questions about the planet's history and geology, but also to search for signs of past life, test the possibility of existence on Martian soil, and lay the groundwork for future colonization. While the Moon and Mars are within our reach, the ultimate challenge is interstellar travel, expeditions to other star systems. One of the most visionary projects in this area is Breakthrough Starshot, an initiative to build a fleet of light-sail spaceships capable of traveling to our nearest stellar neighbors, such as the Alpha Centauri system. These spacecraft could theoretically be accelerated to a significant fraction of the speed of light, allowing them to reach Alpha Centauri in just over 2 decades after launch. Such missions could provide invaluable data on other star systems and potentially habitable exoplanets, paving the way for future interstellar exploration. The journey to the Moon, Mars, and ultimately to the stars is not just a series of missions, but a continuation of our fundamental quest to explore, to understand, and connect with the universe around us. Even stepping into the next chapter of human space exploration can push the boundaries of our technological and scientific capabilities and inspire future generations to dream of the possibilities that lie beyond our cosmic horizon. Beyond the reach of traditional microscopes and within theoretical physics lies a frontier not so much of remoteness as of possibility and understanding. This frontier is challenged not by physical barriers or vast distances, but by the depth of its implications and the invisibility of its scope. Welcome to the quantum realm, where the building blocks of technology and reality behave quite differently from anything we have encountered in our macroscopic world. Quantum mechanics is a phrase that excites the intellect and baffles the mind with its strangeness. Here, particles can exist in several places at once. They can spin in opposite directions at the same time. They can be entangled in the vastness of space, acting in concert with no apparent connection. These bizarre behaviors are at the heart of a technology that could revolutionize our world. Quantum computing. In the heart of this technological storm lies a concept so revolutionary and yet so elusive that it challenges our very perception of information and reality. By traveling the quantum frontier, we enter a space where information is not just processed, but exists in states that defy classical logic. Here, quantum bits, or qubits, can store many possibilities at once, compared to the simple bits of today's digital devices. But how to preserve information in a system that loses its essence at the slightest interaction with the environment? And scientists may have some answers to that question, because quantum mechanics does more than just redefine computing. It encourages us to rethink the cosmos, intertwining with the fabric of space and time in enigmatic phenomena such as black holes. These cosmic anomalies are not mere objects, but the key to understanding the quantum puzzles that hold the secrets of the universe's information storage and retrieval systems. Join us on our expedition, an expedition to the frontier of quantum mechanics exploration that may ultimately redefine the meaning of computing, data protection, curing disease, and perhaps understanding the very fabric of reality itself. So you and I are gradually entering a new era of computing that transcends the binary landscape of classical computing, where data is processed as a straight series of zeros and ones. In contrast, quantum computing works with qubits, which can embody zeros, ones, or both at the same time, utilizing special properties of quantum mechanics to perform complex computations at unprecedented speeds. However, the quantum world is as fragile as it is powerful. One of the main challenges in developing quantum computers is creating and maintaining quantum memory. You see, unlike classical digital memory, which can reliably store information and retrieve it at will, quantum memory is extremely fragile. Any interaction with the external environment can cause quantum information, known as quantum states, to decohere, that is, erase the stored data. This is like trying to hold a spinning coin on its edge. This susceptibility stems from the fundamental nature of quantum memory. It's not simply a matter of storing data, but of preserving complex quantum states, which are the basis of the potential of quantum computing. Herein lies the paradox at the heart of quantum computing, the no-cloning theorem. This theorem is a unique rule of the quantum world and states that it's impossible to create an exact copy of an unknown quantum state. In the everyday world, if you want to prevent data loss, you can make copies of it. But in quantum computing, it's impossible to make an exact copy of a qubit containing unknown information. This rule is a serious obstacle because it means that traditional methods of data protection and error correction, such as backups, simply don't work in the quantum domain. Engineers and physicists are now tasked with developing innovative strategies to combat these problems. They're using quantum error correction techniques that involve entangling qubits, linking them together in complex ways, and allowing the system to detect and correct its own errors without having to directly measure the quantum state. These methods don't just preserve information, they preserve the very essence of quantum behavior. But how can the very gravity wells where not even light can penetrate and quantum computing be related, you might ask? The intriguing connection between black holes and the burgeoning field of quantum computer science begins with one deep mystery they share in common. Stephen Hawking and Jacob Bekenstein, two titans of theoretical physics, once proposed groundbreaking ideas about black holes that have profound implications for modern quantum computing. In a thought experiment, Hawking hypothesized the black hole information paradox, which poses a profound dilemma. What happens to information when it falls into a black hole? Does it disappear forever, or does it persist in some form? This question is analogous to quantum computing's problems with data integrity and loss. Just as information must be preserved when it crosses the event horizon of a black hole, quantum information must be preserved in the unstable environment of a quantum computer. So how much information can a black hole store? Bekenstein in turn presented the concept that the entropy of a black hole, in fact its information content, is proportional not to its volume, as one might expect, but to the area of its event horizon. But how can a surface store information, you may ask? After all, you need some kind of structure. You need atoms or something else that can store bits of information. Well, it turns out that you can calculate that a black hole stores information in bits. The amount of information is equal to the surface area of the event horizon in Planck square units. Planck units are the smallest measurable scales in the cosmos. These units, named after Max Planck, mark the limits beyond which classical theories of gravity and space begin to break down and quantum effects become dominant. Planck units serve as a bridge in our understanding of quantum and cosmological scales, providing a framework that helps us quantify the universe in the most minuscule dimensions imaginable. So why is the information content of a region of space equal to the surface area surrounding that region and not its volume? Consider this analogy to better understand the unconventional way information is stored in a black hole. Imagine that your room is not just a library, but a magical library where your entire collection of books can be encoded simply on the wallpaper that covers the walls. Here, instead of measuring the volume of the room to determine how much it can hold, we look at the surface area of the walls. This radical idea reflects how black holes store information, but not in their vast void, but on their outer surface, at the event horizon. And this leads us to the holographic principle, which may seem like science fiction, but it is a serious scientific theory inspired by the thermodynamics of black holes. A hologram, colloquially speaking, is a flat surface that contains all the data needed to display a three-dimensional image. If you apply this to the universe, a startling possibility arises. Everything you see around you, from your cup of coffee to the stars in the sky, could be a projection of information encoded on a distant two-dimensional surface. The Won-Maldacena model, known as the Anti-de Sitter Conformal Field Theory Correspondence, or ADS-CFT, goes further. It proposes that the type of universe described by Einstein's theory of gravity, negatively curved and seemingly limitless, could be equivalent to a gravity-free quantum field theory defined at the boundary of that space. Essentially, it's as if there were a boundary at the end of the universe that contained a two-dimensional description of all three-dimensional events occurring in it. This revolutionary idea suggests that our understanding of space and time, however intuitive it may seem, may be an emergent phenomena from a deeper, more fundamental reality. The implications for quantum computing are profound. By mimicking the natural holographic data storage observed in black holes, engineers will be able to create quantum systems that are both stable and powerful, capable of performing computations impossible for classical computers. As we move closer to mastering quantum computing, its impact on our future is becoming increasingly clear and promising. This technology doesn't just increase the speed of data processing, It expands our ability to solve problems previously thought unsolvable. Cryptography, medicine, and space exploration are just the beginning. In the field of cryptography, quantum computing is a double-edged sword. On the one hand, they pose a significant threat to existing encryption methods. Traditional security protocols rely on the complexity of factorizing large numbers, for which quantum computers are exceptionally well suited. This capability means that most existing encryption methods can become obsolete over time, leaving data vulnerable, from your personal correspondence to access to your bank account. However, this same ability opens up the potential for quantum cryptography, which can provide a level of security that's fundamentally unbreakable. Quantum key distribution uses the principles of quantum mechanics to create secure communication channels. Unlike traditional keys, any attempt to eavesdrop on quantum keys changes their state, thereby revealing the presence of an attacker. This method could revolutionize the transmission of sensitive information, making our data secure against even the most sophisticated attacks. In medicine, the impact of quantum computing could be revolutionary. The ability to accurately model molecules and biological processes opens new horizons in drug development. Currently, the development of new drugs is a long and expensive process, often taking more than a decade. Quantum computers can significantly speed up this process by predicting the properties of complex molecules and their interactions with the human body more accurately than ever before. One interesting example is the use of quantum computing to develop treatments by modeling the human lung on a chip. This innovative approach, developed by a Swiss startup, uses quantum computing to model human lung cells on a microchip. These cells can be mechanically activated to mimic the behavior of a real lung, allowing researchers to observe how drugs interact with human tissue in real time. Imagine a world in which we can model the human body in minute detail on quantum computers, creating digital twins that doctors can use to test treatments tailored to each patient. This approach could not only speed up the development of new drugs, but also improve their efficacy and safety many times over. It represents a shift towards more personalized medicine, where treatments are optimized for each patient's unique genetic characteristics. Beyond healthcare, quantum computing also promises to revolutionize energy efficiency across sectors. Its ability to solve complex logistical problems and optimize systems can lead to more efficient use of resources. For example, quantum algorithms have already improved cargo movement at the Port of Los Angeles, increasing throughput and reducing energy consumption. Space exploration can also benefit greatly from quantum computing. Navigating vast expanses of space requires processing vast amounts of data for trajectory alignment, system diagnostics, and life support management. Quantum computers could improve the ability of spacecraft to perform these tasks autonomously, making deep space missions more feasible. In addition, quantum technologies can improve our ability to predict and understand space weather, protecting astronauts from harmful radiation, and preserving critical satellite infrastructure. Research into black holes and quantum mechanics is not just a theoretical fad. It's shaping the very tools we expect to revolutionize our future. The insights gained from studying these cosmic mysteries are helping to inform and advance algorithms that will one day be able to manage our data, cure our diseases, and even guide our research into the uncharted reaches of the cosmos. So, quanta, in simple terms, are the smallest possible units of any physical property involved in an interaction, such as energy or matter, such as particles and photons. In classical physics, everything seems smooth and continuous, but At the quantum level, things like energy move in tiny, discrete packets, i.e. quanta, and that's why there are quite a few different methods of quantum computing, each exploring unique approaches to using these tiny units to generate enormous computing power. One of the leading techniques in current quantum computing research involves superconducting circuits. Companies such as Google, IBM, and Rigetti are investing heavily in this technology, which uses supercooled circuits to minimize energy loss and maximize efficiency. These circuits operate at temperatures near absolute zero, allowing quantum states to persist long enough to perform complex computations. Another well-known method uses trapped ions and qubits. Companies such as IonQ and Quantinuum use this technique, where ions are held in space using electromagnetic fields and manipulated with lasers to perform quantum operations. This method boasts longer coherence times, meaning that quantum states remain stable for longer periods of time, although the speed of operation is generally slower compared to superconducting circuits. Photonic quantum computing is also gaining momentum with qubits encoded using photons, particles of light. This approach, promoted by companies such as Xanadu and startups affiliated with academic groups, operates at room temperature and uses the properties of light to perform quantum computing. Recent advances include Xanadu's development of a Borealis chip, which uses a novel method of manipulating groups of photons to gain quantum advantages. In turn, topological quantum computing, which has emerged from a more theoretical framework, offers a new approach to utilizing quasi-particles, particles that arise from interactions within a material. Microsoft's been a key player in this field, exploring ways to create and manipulate these quasi-particles to create qubits that are naturally immune to external perturbations, potentially solving the problem of quantum decoherence. In addition, one quite revolutionary approach to quantum computing is rapidly gaining momentum. This new method, using atoms held in optical tweezers, represents a significant leap forward in our quest to harness quantum mechanics for computing power. Let's take a closer look at this innovative technology and learn how it has the potential to revolutionize the field. Optical tweezers, a tool that uses focused laser beams to capture and manipulate particles, are nothing new in physics, but their application in quantum computing is a new and rapidly developing frontier. By using lasers to capture individual atoms, scientists create qubits that are less susceptible to interference and easier to control than traditional methods. This technique is based on the unique properties of atoms. Being small and electrically neutral, they naturally avoid mutual interference that interferes with other types of quantum bits. This reduction in noise and interference is crucial to maintaining the coherence of quantum information, which is an ongoing challenge in quantum computing. A recent breakthrough in February this year involved the use of micro-lens arrays, which allow a significant increase in the number of atoms that can be manipulated simultaneously. These arrays allow thousands of atoms to be precisely arranged in regular order, each held in place by its own microscopic laser trap. Researchers have successfully used this technique to arrange more than 1,000 atoms with remarkable precision. And these atoms are not just statically held, they are dynamically controlled, ready to perform complex quantum operations. The term supercharging accurately describes the improvement this method brings to quantum computing. By aligning two layers of micro-lens arrays and superimposing laser traps on them, scientists create a dense grid of atomic qubits. This arrangement not only increases the initial number of qubits, but also improves their overall stability and homogeneity. Each atom trapped by this method can potentially serve as a quantum bit. The precision of this approach allows each qubit to be individually addressed and manipulated, opening the way to complex and large-scale quantum algorithms that were previously unattainable When this new method's compared to existing technologies, such as superconducting qubits and ion traps, the atoms in tweezers approach offers significant advantages in scalability and error reduction. Its ability to scale rapidly to thousands of qubits makes it a formidable competitor to better-known technologies. Looking ahead, the potential to scale this technology to 100,000 atoms and beyond is not just optimistic speculation, but a very realistic goal. Achieving this scale could bring quantum computing closer to commercial viability, allowing complex problems, from cryptography to materials science, to be solved. As we conclude our journey through the quantum frontier, we find ourselves at a pivotal moment where quantum computing is moving from theoretical research to practical applications. The X Prize Quantum Applications Competition epitomizes this transition, presenting a challenge with a significant $5 million incentive to spur innovations that apply quantum computing to real-world problems. Over the next 3 years, teams from around the world will explore and demonstrate how quantum technologies can revolutionize healthcare, material science, energy, and other fields. This initiative not only accelerates the development of quantum technologies, but also emphasizes the potential of quantum computing to solve humanity's most urgent problems. By pushing the boundaries of quantum computer capabilities, X Prize aims to stimulate the transition from experimental quantum applications to everyday tools, making the fields of quantum mechanics accessible and useful to society at large. You've probably heard of dark matter, the elusive substance that makes up about 1/4 of the universe. That ghostly puppeteer is pulling the strings of the galaxy but never showing itself. But what if dark matter is just the tip of the cosmic iceberg? Imagine a universe where the scales of gravity tip in mysterious ways, where stars and binary systems, two stars orbiting a common center, defy the very laws established by Newton and Einstein. What if their equations are not the final word? Recent research suggests anomalies and deviations in the orbital dance of double stars that neither dark matter nor our current understanding of gravity can fully explain. So, are we on the cusp of a paradigm shift? Is our view of the cosmos not as stable as we thought? In cosmic ballet, stars are the prima donnas that catch our eye. But have you ever wondered how these celestial luminaries come into being? It all starts in the dark, cold corners of a nebula, a vast cloud of gas and dust. Gravity plays a key role here, pulling the particles closer and closer until they no longer resist gravity. They merge, triggering a nuclear fusion reaction that produces a star. However, the life of a star does not last forever. There comes a point when the nuclear fuel runs out, and the star faces its inevitable demise. For massive stars, this end is nothing short of spectacular. A supernova explosion that eclipses entire galaxies, if only for a short time. These supernovae are not just cosmic fireworks. They are the forges of the universe. It's in the crucible of these explosions that elements heavier than iron are created. So the gold in your jewelry, the calcium in your bones, it's all stardust. The remnants of a supernova explosion. But here's where the plot gets twisted. In a universe dominated by dark matter, these stars and their explosive deaths are part of a larger scene. Dark matter, with its gravitational pull, influences the formation of galaxies and the distribution of stars within them. Imagine two galaxies, one with dark matter and one without. In the galaxy with dark matter, the gravitational forces are so strong that they can cause bursts of star formation, leading to a higher number of supernovae. In these galaxies, stars form and die at an accelerated rate, creating a dynamic and ever-changing landscape. Recent studies have even quantified this relationship, showing a direct correlation between the amount of dark matter in a galaxy and the rate of star formation. But what if this correlation is not as simple as it seems? Enter Mond, modified Newtonian dynamics. This theory suggests that gravity behaves differently at very small accelerations. If Mond is correct, the high rate of star formation in dark matter-rich galaxies may have an alternative explanation. Double star systems, those cosmic pairs we discussed earlier, can serve as an ideal test laboratory for these theories. Their orbital dynamics can show whether Newtonian gravity persists or whether Mond offers a better explanation. As scientists delve deeper into the data, especially the treasure trove provided by the Gaia mission, we're getting closer to understanding the true nature of this galactic dance. In cosmic narratives, dark matter is often portrayed as a silent, mysterious entity that shapes galaxies but remains elusive. One of the most compelling theories attempting to solve this mystery is the cold dark matter model, or CDM. In the CDM model, dark matter is cold, which means that its particles move much slower than the speed of light. This slowness allows them to clump together to form the gravitational scaffolding on which galaxies are built. CDM-based computer modeling has been extremely successful in reconstructing the large-scale structure of the universe. It shows a cosmic network of galaxies connected by dark matter filaments that's very similar to what we observe. But, like any good story, there are unexpected plot twists. While CDM does an excellent job of explaining the grand architecture of the universe, it falters when we get closer to individual galaxies. Take, for example, the rotation curves of galaxies, the speed at which stars and gas rotate around the galactic center. According to Newtonian physics and the CDM model, this speed should drop sharply as we move away from the center. But observations tell a different story. The rotation curves remain surprisingly flat, suggesting that something else is involved here. Perhaps another kind of dark matter, or even a modification of gravity. And then there are dwarf galaxies, smaller satellites of larger galaxies like our Milky Way. The CDM model predicts many of these dwarf galaxies, but we just don't see as many as expected. These inconsistencies have led scientists to consider alternatives and question the very basis of the CDM model. Could it be incomplete, or are we missing an important piece of the cosmic puzzle? This is where Mond enters the scene again, offering a different set of equations that better explain these galactic features. It's like two different scripts of the same movie, each with its interpretation of the main character, dark matter. At check weighing, the scientific community is divided. Is the CDM the final theory that unifies our understanding of the universe, or is it just a stepping stone toward a more complete model? For centuries, Sir Isaac Newton's equations have been the foundation of our understanding of gravity. They've been tested, retested, and retested, and have stood the test of time. But what if there is more to the story? Introducing Mond, or Modified Newtonian Dynamics, a theory that dares to modify Newton's sacred equations. It suggests that gravity behaves differently at extremely low accelerations, such as at the outskirts of galaxies. The goal of Mond, conceived by physicist Mordecai Milgrom in the early 1980s, is to resolve some of the inconsistencies that have arisen in our observations of galaxies, especially those puzzling rotation curves we discussed earlier. You see, Mond fits the observed flat rotation curves of galaxies perfectly, without resorting to dark matter. It's as if Mond is saying, wait, maybe you don't need to invent a mysterious form of matter. Maybe you just need to adjust your equations. And it's not just about rotation curves. Mond has also managed to explain the dynamics of some galaxy clusters and even the large-scale structure of the universe without relying on the mysterious dark matter. But of course, no theory is without problems. While Mond succeeds in some areas, it faces difficulties in others, such as explaining the cosmic microwave background afterglow of the Big Bang. The cosmic microwave background, or CMB, is a snapshot of the universe just 380,000 years after the Big Bang. The CDM model, with its dark matter component, explains the features of the relic radiation well. Mond, however, has difficulties here. And let's not forget our celestial pairs, double star systems. Recent studies, some of which we've already discussed, have shown contradictory results when applying Mond to double stars. So what does that give us? Well, at the very least, a state of exciting uncertainty. As new data comes in, especially from the Gaia mission, Mond continues to be hotly debated. Is Mond the missing piece of the puzzle that will finally explain the anomalies we observe? Or is it a useful but ultimately flawed stepping stone towards a more complete theory? In a universe full of questions, sometimes the answers lie closer to home. Just 1.5 million kilometers from Earth orbits Gaia, a spacecraft that may hold the keys to some of the universe's most puzzling mysteries. Launched by the European Space Agency in 2013, Gaia is no ordinary telescope. It's a space cartographer mapping the positions, distances, and motions of more than 1 billion stars with unprecedented accuracy. Imagine having the coordinates of 1 billion stars at your fingertips. It's like Google Maps for the Milky Way, but with a staggering level of detail. One of Gaia's key techniques is parallax, an ancient method with a modern interpretation. By observing a star from 2 different points in its orbit, Gaia can triangulate the distance to the star with incredible accuracy. But Gaia is more than just a space explorer, it's a theory tester. Remember those controversial theories about gravity and dark matter? Gaia data can be used to put those theories under the microscope. Take, for example, double star systems. These systems are crucial for testing theories like Mond. Gaia's precise measurements of the positions and velocities of these stars can help us understand which theory is correct. And it's not just stars. Gaia also observes asteroids, planets, and even distant galaxies. Its data have been used to refine the Hubble constant, a key parameter that helps us understand the expansion rate of the universe. Measuring the Hubble constant with Gaia has added a new twist to the ongoing cosmic controversy. Different methods yielded slightly different values, and Gaia's data became an important piece of this cosmic puzzle. But the Gaia mission is not without its challenges. While the spacecraft provides a wealth of data, interpreting that data is a different story. The same Gaia data have been used to both support and refute theories such as CDM and Mond, leading to heated debates in the scientific community. It's like a high-resolution photograph where everyone sees something different. Is it a speck on the lens or a revolutionary discovery? Interpretation depends on sophisticated statistical methods and, of course, on our basic assumptions about the universe. There is nothing more fascinating than double stars. 2 stars locked in a gravitational embrace, orbiting each other in a delicate balance of attraction and repulsion. As we mentioned earlier, these dual systems are not just celestial spectacles. They are cosmic laboratories. Here, in the intricate ballet of their orbits, we can test our deepest theories about the nature of gravity itself. Double stars have been a cornerstone of astronomical research for centuries. They've helped us measure the mass of stars, understand stellar evolution, and even confirm Einstein's general theory of relativity. But in the context of our ongoing debate between cold, dark matter and modified Newtonian dynamics, double stars play an even more important role. Their orbital dynamics can reveal whether Newtonian gravity persists or whether Mond offers a better explanation. Recent studies have delved deeper into this question. Some studies, using data from the Gaia mission, have shown that double star systems behave as predicted by Newtonian gravity, casting doubt on the applicability of Mond. However, other studies tell a different story. They suggest that Mond is better suited for some double systems, especially those with large distances between them and weak gravitational attraction. Could it be that both theories are partially correct? Or are we missing a key piece of the puzzle? The scientific community is divided, and for good reason. The stakes are high. The behavior of double stars could either confirm our current theories or send us back to the drawing board in our quest to understand the universe. So, how do we weigh evidence? Meet Bayesian statistics, a mathematical framework that might just tip the scales. Named after Thomas Bayes, an 18th century statistician and theologian, Bayesian statistics offers a way to update our beliefs in light of new data. It's like a mathematical expression of the scientific method itself. Here's how it works. You start with a prior belief, or prior, which is your initial hypothesis. As new data becomes available, you update it before forming a posterior hypothesis, a revised hypothesis that better fits the actual data. In the context of our cosmic debate, be it cold, dark matter, Mond, or something completely different, Bayesian statistics provides a rigorous way to assess which theory is more likely, given the observed data. For example, when analyzing double star systems, Bayesian methods can help quantify the probability that Mond or Newtonian gravity is the correct theory. It's not just about curve fitting, it's about estimating the weight of evidence. And it doesn't just apply to double stars. Bayesian statistics have been applied to a wide range of cosmic phenomena, from the distribution of dark matter in galaxy clusters to the rate of expansion of the universe. Nevertheless, Bayesian methods are not without critics. One of the most controversial points is the choice of a prior. How to choose the initial hypothesis in a way that does not distort the result. The choice of a prior can be controversial because it can affect the results. If your prior leans strongly towards one theory, a posterior may confirm that theory even if the other is equally true. As we grapple with these questions, Bayesian statistics remain a powerful tool in our analytical arsenal. It offers a way to make sense of complex spatial data, sift through the noise, and find the signal. The universe seems to refuse to reveal its secrets readily. Even as we gather more data, the debate about the true nature of gravity is intensifying. Hyun Che, an astronomer who recently hit the headlines, said, quote, "I was feeling like I was dreaming. It seemed so unreal. This is because my results did not match any previous results." Che's work stirred the pot by suggesting that when the gravitational acceleration of stars in certain double systems falls below a certain threshold, they're more consistent with Mond models than with the standard gravity model. But here's the rub. Che's findings contradict several previous studies. He mentions, quote, "One group has been claiming an anomaly for some time, but the anomaly seemed not to match well the predictions of existing modified gravity theories." This discrepancy in results is not just a glitch. It's a fundamental challenge to our understanding of the cosmos. It raises questions about the reliability of our models and the data we use to test them. So what does that give us? Well, at least a state of productive confusion. As Che concludes, quote, because the standard cosmology is based on general relativity, cosmology needs a major revision now. The debate is far from over. As we collect more data and refine our theories, the search for the ultimate truth about gravity and the universe continues. And in this quest, every anomaly, every contradictory result adds a new level of complexity and wonder. For centuries, we've gazed into the night sky, listening to the stories told by the light of the distant stars. We've built telescopes to see deeper and farther, to uncover the secrets hidden within the cosmos. But light is only part of the story. There is another, more subtle language that the universe speaks. A language of ripples and echoes written into the very fabric of space and time. Welcome to the era of gravitational wave astronomy. Gravitational waves are ripples in the fabric of space-time, predicted over a century ago by Albert Einstein. Unlike electromagnetic waves, such as light, radio, or X-rays, which are vibrations of electric and magnetic fields, gravitational waves are distortions in the very structure of space and time itself. They're created by some of the most violent and energetic events in the universe. Einstein's general theory of relativity, published in 1915, proposed that massive objects like stars and planets don't simply exist in space, they warp and curve it. This distortion is what we perceive as gravity. But Einstein went further. He suggested that when these massive objects accelerate, when they move, collide, or explode, they create ripples in space-time. Much like a stone thrown into a pond creates ripples on the water's surface. Gravitational waves are produced by cataclysmic events, collisions of black holes, explosions of supernovae, the merging of neutron stars. These waves travel across the universe at the speed of light, carrying with them information about the events that created them. They tell us about the nature of gravity, the properties of black holes, and the birth of stars. But gravitational waves are incredibly weak by the time they reach us. Having traveled billions of light years across space, detecting them requires instruments of unprecedented sensitivity, machines capable of measuring changes of distance smaller than a fraction of the width of a proton. This is the challenge that scientists have faced for decades. In the 1990s, a new generation of scientists set out to build such an instrument. The result was LIGO, the Laser Interferometer Gravitational Wave Observatory. It consists of two massive detectors, one in Washington and the other in Louisiana, that are designed to detect these faint ripples in space-time. Their construction marked the beginning of a new era in the search for gravitational waves. Gravitational waves don't just pass through the vast reaches of space, they also pass through us. As these waves travel across the universe, they stretch and squeeze the space they move through, causing distances between objects to change. But the question arises, do gravitational waves stretch us too? In theory, yes. Gravitational waves do stretch and compress everything in their path, including us. However, the effect is incredibly tiny. A passing gravitational wave would stretch you by less than the width of an atomic nucleus. It's so small that it can't be felt or noticed by us in any way. At LIGO, the world's most precise measuring device, a laser interferometer is used to detect these minuscule changes. The device splits a laser beam and sends the two halves down perpendicular arms, each several kilometers long. When a gravitational wave passes by, it changes the length of these arms by a tiny amount, altering the interference patterns of the light. This change indicates that a gravitational wave has passed. Thus, while gravitational waves do indeed stretch us, their effects are so minute that they can only be detected by the most advanced technology, like the instruments at LIGO. Through these ultra-precise measurements, we're able to hear the faint whispers of the universe. Gravitational waves are not just distortions in space-time. They also carry energy. When massive objects like black holes merge, they release an enormous amount of energy in the form of gravitational waves. This energy travels across the cosmos, rippling through space-time and revealing the most powerful events in the universe. The first detection by LIGO in 2015 confirmed that these waves carry energy away from their source, causing the black holes to spiral towards each other and eventually merge. The amount of energy carried by these waves is staggering. In just a fraction of a second, the merging black holes emitted more energy than all the stars in the observable universe combined. This discovery not only confirmed Einstein's theory, but also opened a new way to understand the most energetic processes in the universe, revealing information about the objects and events that created these waves. Each detection tells a story of the formation and evolution of black holes, neutron stars, and even entire galaxies. The energy carried by gravitational waves does more than just stretch space. It allows us to map the universe's most extreme environments, to understand how black holes and neutron stars form, and to explore the very nature of space and time. Gravitational waves not only affect the space they move through, they also have profound effects on the very objects that create them. When two massive objects like black holes merge, the gravitational waves they emit carry away significant amounts of energy. This loss of energy directly impacts the motion and structure of the black holes themselves. When neutron stars collide, the effects are even more dramatic. Gravitational waves not only strip away energy but also determine the final outcome of the collision. Whether a new, more massive neutron star is formed, or whether the stars collapse into a black hole. These waves provide clues about the internal structure and composition of these dense, enigmatic objects. The gravitational waves we detect are signals from the heart of cosmic violence, revealing the forces at play, the incredible energies involved, and the final fate of these cosmic giants. They help us understand how stars live and die, how black holes are born, and how matter behaves in the most extreme environments imaginable. To detect gravitational waves, scientists needed to build an instrument unlike any other: the Laser Interferometer Gravitational Wave Observatory, or LIGO. Its design is based on a simple but powerful idea: using light to measure the tiniest distortions in space. The principle behind LIGO is simple in concept, but complex in execution. A powerful laser beam is split into two, sending the light down two long arms, each 4 kilometers in length. At the end of each arm, mirrors reflect the light back to the central beam splitter, where the two beams are recombined. In the absence of a gravitational wave, the beams cancel each other out perfectly due to their carefully calibrated paths. However, when a gravitational wave passes through Earth, it stretches space in one direction while compressing it in the perpendicular direction. This changes the length of the arms, altering the time it takes for the laser beams to return, creating a distinctive interference pattern that LIGO's detectors can measure. To detect these incredibly small changes, LIGO must operate under extreme conditions. The entire interferometer is housed in ultra-high vacuum tubes to eliminate air molecules that could scatter the laser light. The mirrors are suspended by finely tuned systems that isolate them from ground vibrations caused by traffic, wind, or distant earthquakes. LIGO is not alone in its quest to detect gravitational waves. Across the globe, a network of observatories works together to listen to the universe, combining their data to improve the precision and reliability of detections. Virgo, located near Pisa, Italy, is LIGO's European counterpart. With its 3-kilometer-long arms, Virgo uses the same principles of laser interferometry to detect gravitational waves. By collaborating with LIGO, Virgo helps pinpoint the location of cosmic events, allowing astronomers to direct their telescopes to the right portion of the sky at the right time. In Japan, the Kagra Observatory brings new innovations to the field. Located deep underground to shield it from surface noise, Kagra also uses cryogenically cooled mirrors to reduce thermal vibrations, making it even more sensitive to gravitational waves. By combining data from detectors on different continents, we can determine the location of gravitational wave sources with much greater accuracy. When a gravitational wave passes through Earth, it arrives at each observatory at slightly different times. By measuring these time differences, we can pinpoint the source of the waves in the sky. This global network has enabled us to conduct multi-messenger astronomy, where gravitational waves are observed alongside light, radio waves, and gamma rays. Together, they paint a fuller picture of the most extreme cosmic events. Gravitational wave astronomy is truly a global effort. Scientists from every corner of the world are working together to unlock the universe's secrets, proving that in science, collaboration knows no borders. Gravitational waves come in a wide range of frequencies, and each frequency reveals a different story about the universe. LIGO and its partner observatories are tuned to capture specific frequencies that align with some of the most energetic events in the cosmos. LIGO is designed to detect gravitational waves in the frequency range of approximately 10 Hz to 10,000 Hz. This range is well suited for capturing waves produced by events like the merging of stellar mass black holes or the collisions of neutron stars. These frequencies fall within a range similar to that of human hearing, but instead of sound waves traveling through air, they are ripples traveling through space-time. Each gravitational wave signal can tell us about the objects that created it. For example, a merger of two black holes produces a chirp, a wave pattern that increases in frequency and amplitude as the black holes spiral closer together, culminating in a sudden peak as they merge. The unique signature of each chirp allows scientists to determine the masses, spins, and distances of the merging objects. However, not all gravitational waves fall within LIGO's detection range. Lower frequency waves, such as those produced by the mergers of supermassive black holes found in the centers of galaxies, lie outside LIGO's current capabilities. Detecting these lower frequency waves requires different types of instruments. And this is where the future of gravitational wave astronomy comes into play. The planned Laser Interferometer Space Antenna, or LISA, will be positioned in space to detect these lower frequency gravitational waves. By expanding our observational range, Lisa will allow us to hear the deep, slow rumblings of supermassive black hole mergers and other cosmic phenomena to further extend our understanding of the universe. By broadening the range of detectable frequencies, we'll open up new windows into the universe, enabling discoveries from high-pitched chirps of merging neutron stars to the low-frequency growls of supermassive black holes colliding. Each new frequency band brings with it new opportunities for understanding the cosmos. In August 2017, a groundbreaking moment in astronomy took place. For the first time in history, an astronomical event was observed in both gravitational waves and electromagnetic radiation. This event, known as GW 170-817, marked the dawn of multi-messenger astronomy. GW 170-817 was the merger of two neutron stars, the remnants of massive stars that had previously exploded as supernovae. As these neutron stars spiraled together, they emitted gravitational waves detected by LIGO and Virgo. Just 1.7 seconds later, NASA's Fermi Gamma Ray Space Telescope observed a burst of gamma rays, pinpointing the event's location in the sky. This unique observation triggered an unprecedented global effort. Within hours, dozens of telescopes across the planet began observing the region in different wavelengths, from radio to X-rays, allowing scientists to study the event in detail like never before. This first-ever joint observation provided critical insights into the universe's workings. It confirmed that neutron star mergers are key sites for producing heavy elements, such as gold and platinum, and scattering them throughout the cosmos. This was a long-suspected theory, now proven with direct evidence from gravitational waves. The discovery of GW 170-817 demonstrated the immense power of combining gravitational wave and electromagnetic observations, allowing us to witness cosmic events with greater clarity and precision. It opened a new window into the universe, where every detection tells a deeper, richer story. Multi-messenger astronomy represents a new era of discovery, where light and gravitational waves together illuminate some of the most profound mysteries of the cosmos. Gravitational wave astronomy is still in its infancy, but its potential is vast. What could we uncover in the coming years and decades? What new mysteries of the cosmos might we solve? With more sensitive detectors and more powerful instruments, we might soon detect gravitational waves from sources we've never observed before. Could we hear the faint echoes of the Big Bang, confirming theories about the earliest moments of the universe? Detecting these primordial waves could provide direct evidence of cosmic inflation, the rapid expansion of the universe just moments after the Big Bang. It could answer questions about the fundamental forces that shape the cosmos. Gravitational wave astronomy could also reveal unknown phenomena, objects or events that we've never imagined, exotic forms of matter, hidden dimensions, or the mysterious dark matter that makes up most of the universe's mass. Gravitational waves could help uncover these elusive secrets. We're standing at the edge of discovery, poised to answer some of the most profound questions ever asked about our universe. Gravitational wave astronomy offers a new way to explore the cosmos, opening a path to discoveries beyond our wildest dreams. The universe is full of whispers, and we are just beginning to listen. Saturn has captivated the human imagination. From ancient civilizations to modern astronomers, the Maori of New Zealand, separated by vast oceans and without telescopes, somehow knew that Saturn had rings. How? The mystery deepens. Saturn has long been a symbol of the unknown and mysterious. Its iconic rings have been the subject of wonder and speculation since the time of Galileo. But what if we told you that these rings, however eternal they may seem, are actually a fleeting cosmic phenomenon? Adding to the intrigue is a storm twice the width of Earth, with a mysterious hexagonal shape that's raging at Saturn's North Pole. What forces could have created such a geometrically perfect formation? But the mysteries don't end there. Saturn's satellites, Titan and Enceladus, offer conditions that could potentially support life. Lakes of liquid methane and geysers spewing water and organic material into space make these satellites more than just celestial bodies. They're potential homes for life. Join us for a closer look at this enigmatic giant and its cosmic mysteries. Our journey begins with Galileo Galilei, the Italian astronomer who first pointed his telescope at Saturn in 1610. What he saw puzzled him, a planet with something like ears. He didn't realize he was looking at the edges of Saturn's magnificent rings, a feature that would puzzle astronomers for centuries to come. Galileo's telescope was primitive by today's standards, and the true nature of Saturn's ears remained a mystery. It was not until 1655 that Christian Huygens, armed with a more advanced telescope, correctly identified them as a system of rings surrounding the planet. Moving into the modern era, we witnessed the Pioneer 11 mission, the first spacecraft to fly past Saturn in 1979. This mission provided us with the first close-up images of the planet and its rings, revealing intricate details that were once inaccessible to Earth's telescopes and us. But it was the Cassini mission that truly revealed Saturn in all its glory. Launched in 1997 and arriving at Saturn in 2004, Cassini spent 13 years studying the planet, its rings, and its satellites. From discovering plumes of water ice on Enceladus to capturing the ethereal beauty of a hexagonal-shaped storm at Saturn's North Pole, Cassini revolutionized our understanding of this distant world. And here's an interesting point. Long before the advent of telescopes, the Maori people of New Zealand had myths that described Saturn as having a parero, or belt, around it. How they knew this remains a matter of debate and speculation. But as we'll see later, Saturn holds more than one mystery. What do you think could have created a hexagonal storm with an area larger than the Earth itself? Saturn harbors a geometric enigma at its North Pole, a six-sided storm that's puzzled scientists for decades. This six-sided wonder is not just a superficial feature, but a deep and enduring mystery that breaks down the understanding of fluid dynamics and planetary atmospheres. The hexagon was first discovered in 1981 by the Voyager spacecraft. But it wasn't until the Cassini mission, which orbited Saturn from 2004 to 2017, that we got a front-row seat to this cosmic spectacle. Cassini's high-resolution images showed a symmetrical jet stream surrounding the hurricane-like vortex at the center of the hexagon. Unlike Earth's chaotic weather systems, Saturn's hexagon is a masterpiece of geometric precision. So what's causing this hexagonal storm? Researchers at Harvard University have developed a 3D model that suggests deep thermal convection in Saturn's outer layers may be the culprit. This model shows that the storm could spread thousands of kilometers deep into Saturn's atmosphere, well beyond what we can see. Interestingly, scientists have been able to reproduce the hexagonal pattern in a laboratory setting. Although these experiments do not capture all the nuances of Saturn's complex atmosphere, they provide a glimpse of extraterrestrial phenomena. Saturn's hexagonal vortex contrasts sharply with Earth's polar vortex, which is irregular and less stable. This difference raises questions about the fundamental properties that distinguish the atmospheres of the gas giants from the Earth group planets. The longevity of the hexagon is another mystery. It's been observed for at least 4 decades, and possibly much longer. This steady feature suggests that everything that feeds the hexagon is not a temporary phenomenon, but a stable, perhaps even permanent, aspect of Saturn's internal dynamics. Let's shift our attention from the mystery of the hexagon to another wonder of Saturn. Saturn's rings are more than just celestial jewelry. They're dynamic, ever-changing systems that interest astronomers and the public alike. But what are these rings made of, and why are they so short-lived? Saturn's rings are composed mostly of water ice with a mixture of dust and rocky material. They range in size from tiny particles to huge chunks the size of houses. These ice particles are not static. They're in constant motion under the influence of Saturn's gravity and the gravitational pull of its satellites. The rings are divided into several subdivisions and gaps, each with its own unique characteristics. Most notable are the A, B, and C rings, separated by gaps, such as the Cassini ring, a gap 3,000 miles between the A and B rings. The origin of Saturn's rings has been the subject of debate. One popular theory suggests that they formed from the remnants of a shattered moon. Another theory states that they're the remnants of material from the formation of the solar system, captured by Saturn's gravitational pull. Recent research has also shown that the rings may be much younger than Saturn itself, perhaps around 400 million years old, based on the rate of dust contamination. Saturn's rings don't last forever. They're slowly disappearing because of a phenomenon known as ring rain, in which ring particles are drawn into Saturn's atmosphere. This process is accelerated by micrometeoroid bombardment and interaction with Saturn's magnetic field. At the current rate, some scientists predict that Saturn's rings could disappear within 100 million years. The depletion of the rings would not only change Saturn's appearance, but could also have consequences for its atmosphere and magnetic field. As we pause for a moment, we realize that even the most fascinating features of our universe are not immune to the inexorable forces of physics, doomed to disappear into the chronicle of eternity. Saturn, the ringed giant of our solar system, is not just a celestial wonder. It's also a cosmic playground that contains some of the most intriguing satellites, 2 of which, Titan and Enceladus, have fascinated scientists and sparked debate about the potential for life beyond Earth. Titan, Saturn's largest satellite, is a world shrouded in mystery. Its dense atmosphere is rich in organic compounds, and there are lakes and rivers of liquid methane on the surface. But what's truly amazing is Titan's rate of removal from Saturn, 100 times faster than previously thought, amounting to a staggering 4.3 inches per year. This rapid drift suggests a dynamic and evolving relationship between Titan and Saturn. Could this drift affect Titan's internal dynamics? And perhaps even its potential for the existence of life. An atmosphere rich in organic compounds such as nitrogen and methane, and the possibility of an underground ocean, make Titan a tempting target for the search for extraterrestrial life. But the question remains, what would life look like in an environment so radically different from Earth's? And let's remember Enceladus, another satellite of Saturn that's very different from Titan. It's an icy world with a highly reflective surface that outshines any other body in the solar system. Enceladus takes the concept of an ocean world to a new level. Not only does it have a subsurface ocean, but it also sprays it into space, where samples of it can be collected by a space probe. This ocean contains most of the chemical ingredients necessary for life, including hot, mineral-rich water erupting from hydrothermal vents. hydrothermal vents can provide the necessary conditions for life as we know it. On Earth, these vents are teeming with life forms that thrive in extreme conditions. Could Enceladus's vents be home to similar but alien life forms? Enceladus also contributes to Saturn's E-ring, a unique characteristic that further enriches the dynamic relationship between the Moon and its planet. The icy particles in this ring open a window into the Moon's internal chemistry, providing clues that may reveal its secrets. Titan and Enceladus are two moons orbiting the same planet, but quite different in their characteristics. Both present compelling arguments in favor of the potential for life, fueling our curiosity. As we ponder the possibilities of life on Saturn's satellites, it's worth noting that our curiosity is not limited to telescopes and computer modeling. Upcoming missions aim to study these satellites up close and perhaps answer some of our most pressing questions. Meet Dragonfly, NASA's ambitious mission to Titan. Scheduled for launch in the 2030s, this rotorcraft will fly over Titan's diverse terrain, from dunes to impact craters. Dragonfly's main goal is to search for the building blocks of life. It will analyze complex organic compounds in the atmosphere and on the surface, providing invaluable data on Titan's chemistry. Equipped with a suite of scientific instruments, Dragonfly seeks to understand the geologic processes on the Moon and how they relate to its potential for life. Could Titan's unique chemical composition and liquid methane cycles offer a different recipe for life? Although no missions to Enceladus are currently planned, the Moon's potential for life has made it a prime candidate for future exploration. Scientists are proposing missions that could fly through Enceladus's plumes and directly sample its underground ocean. Such a mission could analyze the chemistry of the plumes in search of signs of life or prebiotic chemistry. The presence of hydrothermal vents in Enceladus's oceans adds another layer of intrigue, suggesting an environment in which life could potentially thrive. Despite the technical challenges, a mission to Enceladus could revolutionize our understanding of the potential for life in the solar system. It could provide direct evidence for the existence of extraterrestrial life, or at least provide clues to the conditions necessary for life to exist. As we mentioned, Saturn's rings don't last forever, as we once thought. Recent studies have shown that a process that can last hundreds of millions of years is causing these icy wonders to slowly fade away. But what significance does this have for Saturn and its complex atmospheric dynamics? According to a study by the Japan Aerospace Exploration Agency, this material, composed mostly of water, causes a decrease in electron density in Saturn's atmosphere. This phenomenon, known as ring rain, significantly affects Saturn's atmospheric conditions. Ring rain is not just a trickle. It's a stream that carries away water in amounts equivalent to an Olympic-sized swimming pool every half hour. Compounding the mystery is the relative youth of Saturn's rings. Although Saturn itself is about 4.6 billion years old, data from NASA's Cassini mission suggests that the rings may be only a few 100 million years old. This leads us to wonder, if Saturn's rings are so young, what catastrophic event could have led to their formation? Was it the destruction of a moon? Or perhaps the capture of a passing comet? Cassini's Space Dust Analyzer has added another layer of complexity. Over 13 years, it's collected 163 dust particles that came from outside the Saturn system. Surprisingly, the rings turned out to be quite clean, suggesting that they hadn't existed long enough to accumulate excess cosmic dust. This cleanliness raises the question, if the rings are young, why haven't they collected more cosmic dust? The absence of cosmic dust in the rings challenges our understanding of their age and their interaction with the wider cosmic environment. It's as if the rings are in a cosmic laboratory room, or clean room, isolated from the dust that permeates the rest of the solar system. As the rings are depleted, Saturn's appearance will undergo a dramatic transformation. These rings have been the planet's hallmark. Their disappearance would not only change Saturn's appearance, but could also have unknown consequences for its atmosphere, perhaps even affecting the planet's albedo and heat retention. The loss of the rings could have a cascading effect on Saturn's atmosphere, potentially altering wind patterns and even affecting the planet's iconic storms. The full extent of these changes is still unknown, making them a subject of intense scientific interest. Interestingly, the fate of Saturn's rings may be inextricably linked to its satellites. Some theories suggest that gravitational instability may have destroyed some of the icy satellites orbiting Saturn, providing enough material to form the rings. Saturn's rings and satellites are like partners in a cosmic dance, each affecting the other in subtle but significant ways. As we continue to study these celestial bodies, we can say unequivocally that the fate of one can shed light on the mysteries of the other. Beneath the surface of our everyday lives, governed by the familiar pull of gravity and the invisible bonds of electromagnetism, lies a hint of something more, something that challenges the established order of forces that shape our reality. For centuries, the human intellect has tried to make sense of the majestic diversity of nature, unraveling thread by thread the laws that govern all things visible and invisible. And yet, as we look ever deeper into the heart of matter and the vast expanse of space, we are increasingly confronted with anomalies, behaviors that defy explanation, phenomena that slip through the cracks of our most trusted theories. This is where the rumor of a fifth force, a force beyond gravity, electromagnetism, and nuclear interactions, originates. So today we decided to ask, how possible is the existence of this fifth architect of the universe, forming the very essence of matter and energy? First, let's start with the basics to make sure we're all on the same page. 4 fundamental forces are at work in the vastness of the universe, each playing its unique role, shaping everything from the microcosm of subatomic particles to the macrocosm of galaxies. Gravity, often considered the force most familiar to us, dictates the motion of planets and stars, causing celestial bodies to move in their orbits. It's the same force that keeps our feet on Earth and makes apples fall from the tree. Next, we'll look at electromagnetism. This force is responsible for the glow of auroras, the brilliance of stars, and the very light traveling through the vastness of space to meet our eyes. Electromagnetism controls the interaction of charged particles, creating everything from palpable warmth of sunlight to the invisible waves that carry our voices through the air. Another force at the heart of every atom is the strong nuclear force. It reigns supreme within the atomic nucleus, ensuring protons and neutrons remain locked in a strong bond. This force is the reason for the existence of the glowing of the sun and the grandest explosions in the universe, supernovae. Although limited in range, it is the key to the immense power of stars, driving thermonuclear reactions. Finally, we encounter the weak nuclear force, a subtle shaper of the elements. The weak nuclear force plays a crucial role in the nuclear processes that power stars and lead to the synthesis of various elements. This force is necessary for the sun to shine and for the very existence of elements beyond hydrogen in the periodic table. These 4 forces describe the complex interaction of matter and energy that dictates the universe's structure, behavior, and evolution. Understanding them is essential to understanding the fundamental principles governing our world. In the realm of infinitesimals, where atoms are their universes, 4 fundamental forces manifest their influence uniquely. The strong and weak nuclear forces acting within the atomic nucleus are central to this scale. The strong nuclear force, with its iron grip, ensures the stability of the atomic nucleus. This force is so powerful that it overcomes the repulsion between positively charged protons, binding them with neutrons to form the nucleus, the heart of every atom. Though powerful, this force is remarkably short-ranged. Its influence barely extends beyond the nucleus. Meanwhile, the weak nuclear force makes itself known through beta decay, transforming a neutron into a proton, while emitting an electron and an antineutrino. Although weaker and short-lived than the strong nuclear force, this force plays a key role in the alchemical transformations within stars, helping to synthesize the elements that make up our world. Translating our view of the celestial interaction of planets and stars, gravity and electromagnetism begin to dominate the scene. Overarching gravity governs the orbits of planets around stars, holds moons bound to planets, and gives structure to galaxies. Electromagnetism, on the other hand, is the architect of light. From the violent flares of the sun to the serene glow of distant stars, this force generates the entire electromagnetic spectrum, from radio waves to gamma rays, providing the visibility of the cosmos and the fundamental interactions between charged particles in its vastness. On the largest scales of galactic superclusters, gravity is the undisputed ruler. It weaves together the fabric of the cosmos and dictates the motion of galaxies and the structure of the universe itself. However, things have become much more complicated than we previously thought. Scientists continue to encounter phenomena that defy our established quartet of forces. These anomalies suggest the existence of a force beyond gravity, electromagnetism, and nuclear interactions. One such mystery arose in the bowels of particle physics. In the late 20th century, experiments designed to investigate the characteristics of fundamental particles began to reveal inconsistencies. Measurements of the decay rates of some particles and the gravitational behavior of objects on microscopic scales hinted at effects not accounted for by the standard model of particle physics. Even pioneers such as Ettore Majorana and Julian Schwinger suggested the existence of additional forces, and their theories offered the first mathematical framework to account for these anomalies. Schwinger, in particular, proposed a fifth force with a small radius of action that could subtly influence the interaction of particles and yet be undetectable in broader gravitational measurements. Subsequent studies highlighted several anomalies that current theories of physics cannot fully explain. A reanalysis of the Ethvos experiment by Professor Fishback and his colleagues back in 1986 revealed inconsistencies in gravitational acceleration that depended on the composition of materials, indicating non-Newtonian coupling. Similarly, in the 1996 revisit by Fishback and Talmage, the motivation for studying the fifth force was the recognition that some experimental results could not be explained by known forces, including gravitational anomalies and deviations in kaon regeneration experiments that hinted at an anomalous energy dependence that could arise from an external field. The initial speculation around the fifth force was driven mainly by a desire to explain these anomalies. The hypothesis suggested the existence of a new medium-range force, similar to gravity, arising from the exchange of a new ultralight boson. This boson was based on numerous Planck scale theories predicting such bosonic fields, altering the usual gravitational interaction between masses. Subsequent studies aimed to find new theories and hypotheses to explain the observed anomalies and further test the fifth force hypothesis. They consider the influence of a massive hypercharged field, proposing the exchange of hyperphotons to create a potential that could explain the anomalies observed in the Ethos experiment. Despite the lack of conclusive evidence for such a force, continuing anomalies in the experimental data and the predictions of various unifying theories leave the search for a fifth force an open question. The search for a fifth power has gained new momentum in recent years. The Atomki experiment, led by scientists from the Hungarian Academy of Sciences, has revealed one of the most tantalizing hints. Observing an unexpected anomaly in the decay of beryllium-8 atoms suggested the influence of a force not predicted by existing theories, a potential carrier particle called the X-17 boson. This discovery has sparked a flurry of theoretical work, with physicists worldwide proposing new models to explain the Atomki anomaly and similar observations. Theories involving dark photons, photophobic forces, and hidden sectors of the universe have emerged, each trying to weave these anomalies into a coherent narrative. Around the world, advanced research centers have become springboards for this monumental quest. From the vast CERN complex, home to the colossal Large Hadron Collider, to the intricate underground labyrinths that house the ultra-sensitive detectors of the Lux-Zeppelin dark matter experiment. These are modern temples of science. Here, amid the hum of superconducting magnets and the soft glow of computers, physicists push the boundaries of the known universe. At the heart of the LHC, amid a maze of tunnels and the hum of accelerating particles, scientists explore the fabric of reality. Here, particles accelerate to near-light speeds and then collide, giving birth to a fleeting microcosm where the laws of physics can be observed in their most primal form. In these high-energy collisions, signs of a fifth force, unveiled in the consequences of subatomic interactions, may lurk. One experiment that shook up conventional wisdom was the observation of anomalous decay of B mesons in the LHCb experiment. These mesons, consisting of a lower quark bound to a lighter quark, exhibited a decay pattern that deviated from the predictions of the standard model. Decay into electrons and muons, particles that should be treated equally by the known forces, showed an unexpected bias. This discrepancy hinted at an unseen influence, perhaps the bearer of a new force, subtly altering the behavior of fundamental particles. On the other side of the Atlantic, Fermilab has embarked on a search using the Muon G-2 experiment. Similar to heavy electrons, muons have a magnetic moment, a property that dictates how they interact with magnetic fields. The standard model of particle physics, a theory that's withstood the scrutiny of countless experiments, predicts this magnetic moment with surprising accuracy. However, the Muon G-2 experiments measured a value that stubbornly disagrees with these predictions. This deviation suggests that muons may be feeling the attraction of an unknown force whose influence eludes our current understanding. The centerpiece of this experiment is the muon, an elementary particle similar to an electron, but with about 200 times the mass. These particles constantly bombard the Earth as a byproduct of cosmic rays striking the atmosphere, making them both ubiquitous and valuable for scientific research. The Muon G-2 experiment is based on the desire to accurately measure the anomalous magnetic dipole moment of the muon, often referred to as the G2 value. This physical quantity reflects the oscillation or precession of the muon under the influence of a magnetic field. The standard model of particle physics, the most reliable framework for understanding the fundamental forces and particles of the universe, offers accurate predictions for this quantity. However, if experimental measurements deviate from these predictions, This may indicate the influence of forces or particles beyond our current theoretical picture.
The magnet used for the Muon G-2 experiment is a superconducting magnet. It has a 50-foot diameter. We run more than 5,000 amps through it, which produces a field of approximately 1.45 Tesla, which is about 30,000 times the magnetic field of the Earth. So it's a very strong magnet.
Inside this magnet, muons are trapped and observed as they cross the magnetic field. However, despite all their power, muons embody the ephemeral nature of the subatomic world. They live only 2.2 microseconds before decaying into electrons and neutrinos. This short lifespan of 2 millionths of a second is a blink of cosmic time, but it is just long enough for physicists to make measurements. By meticulously measuring the precession rate of muons, scientists can compare experimental results with theoretical predictions derived from the Standard Model. The first results of Fermilab's Muon G-2 experiment, published in April 2021, have aroused the scientific community's interest. The measured precession rate of muons showed a significant discrepancy with the predictions of the Standard Model. In particular, the muons oscillated at a higher rate than expected, suggesting the possible influence of unknown particles or forces interacting with the muons. This discrepancy, expressed as a deviation with a statistical significance of 1 in 40,000, means there is a 99.9975% chance that this result is not a simple statistical fluke, but a tangible sign of new physics. The implications of the results of the Muon G-2 experiment extend far into the realm of cosmology and particle physics. If the observed discrepancy is confirmed, it could provide insight into the pervasive mysteries of dark matter, dark energy, and the imbalance between matter and antimatter. In a nutshell, dark matter, which makes up approximately 85% of the matter in the universe, remains undetected in direct experiments, and is known only through its gravitational effects on cosmic structures. Similarly, dark energy, which drives the universe's accelerated expansion, accounts for only 74% of its energy content, and its nature is largely unknown. The asymmetry of matter and antimatter, in turn, raises the question of why the universe is dominated by matter, despite theoretical predictions of equal amounts of matter and antimatter at the origin of the universe. The results of the Muon G-2 experiment may hint at new particles or interactions affecting the behavior of the muon, which may be related to the elusive dark matter or other unknown aspects of the universe. In addition, these results may help study antimatter and the asymmetry between matter and antimatter, shedding light on the conditions that led to the predominance of matter in the universe. In the context of the past successes of the Standard Model, the G-2 muon experiment represents a turning point in the ongoing quest to understand the universe's fundamental structure. The Standard Model has had a profound impact on modern physics, providing significant technological advances and deepening our understanding of the structure of the universe. Can such experiments illuminate the mysteries of dark matter, dark energy, and the asymmetry of matter and antimatter? The G-2 muon experiment could herald a new chapter in our understanding, guiding us toward a more complete theory of the universe. We look forward to further research and confirmation of experiments by scientists in this fundamental area of physics. Imagine a burst of energy so powerful that it eclipsed an entire galaxy for a moment. A burst of unimaginable power that traveled billions of light years to reach us, whose origin is still shrouded in mystery. It's not simply some sort of science fiction. It's the true story of gamma ray bursts, the most energetic events known in the universe. On October 9th, 2022, astronomers discovered something unprecedented. The brightest gamma-ray burst of all time, which they nicknamed BOAT. It was so unusual that it shook nearly all of their previous concepts about these cosmic phenomena. But the story of GRB 2210-09A is not just about brightness, it's about the questions it raises, anomalies in its spectrum, the unexpected absence of heavy elements, and new challenges to our understanding of how the most powerful explosions in the universe happen. What caused this colossal explosion? And what secrets can it reveal about the forces shaping our universe? The universe is a realm of unusual phenomena, some of which challenge the very limits of our understanding. Prominent among them are gamma-ray bursts, GRBs, some of the most powerful and mysterious explosions known to science. Discovered quite by accident in 1967 by U.S. military satellites, gamma-ray bursts were at first a puzzling mystery and cause for concern because of their intense energy release, which were mistaken for nuclear testing. However, as it became clear that their origin was from somewhere in the cosmos, GRBs quickly evolved from being a top-secret mystery to one of the most studied astrophysical phenomena. These bursts are divided into two main types: short GRBs, which last less than 2 seconds, and long GRBs, which can last up to several minutes. This division is not merely academic. It reflects the different underlying physical processes. Short GRBs are usually associated with neutron-star collisions. While long GRBs, like the one observed in October 2022, are associated with a cataclysmic collapse of massive stars. The event in question, dubbed brightest of all time, or BOAT, occurred in the constellation Sagitta. Detected on October 9, 2022, this gamma-ray burst was unlike anything astronomers had ever before observed. Its brightness, 10 times greater than all previously recorded GRBs, shocked the scientific community. What made this event even more amazing was its duration. It lasted 10 minutes, and the afterglow was visible for more than 10 hours. Most outbursts disappear from view within a few seconds or minutes, making BOAT an exceptional event. But beyond the spectacle, the BOAT event has profound implications for our understanding of the universe. Gamma-ray bursts are, by their very nature, windows into extreme conditions that cannot be replicated on Earth. They allow scientists to investigate the fundamental laws of physics, especially when matter is subjected to intense energy and gravitational forces. The BOAT event, so bright and so close, provided a unique opportunity to study these extreme conditions in unprecedented detail. The resulting data opens new avenues for understanding not only gamma-ray bursts, but also the very processes that govern the life and death of stars. The brightest of all time, GRB 2210-09A, then stood out not only for its staggering intensity, but also for its amazing duration. The explosion was so powerful that it was the brightest gamma-ray burst ever recorded, lasted 10 minutes, and left an afterglow visible for more than 10 hours. Such an event at a distance of only 2.4 billion light-years is not just rare, it's almost unprecedented, occurring only once every 10,000 years. What makes this outburst truly unique is the combination of extreme brightness and prolonged visibility. Most GRBs are fleeting, often only detectable for a few seconds or minutes. In contrast, GRB 2210-09A lasted much longer. High-energy emissions lasted for tens of thousands of seconds. This duration provided an unprecedented opportunity for observations and analysis over a wide wavelength spectrum, from X-rays to gamma rays. The BOAT brightness was so intense that it caused saturation effects in numerous scientific instruments. including the GBM, Gamma Burst Monitor, and LAT, Large Area Telescope. These instruments, designed to capture and analyze high-energy photons, were overwhelmed by the power of the event, resulting in significant noise and data delays. Notably, the 400 GeV, giga-electron-volt photon, was detected nearly 10 hours after the initial burst, indicating unusually high energy levels. Despite its stunning brightness and duration, this event also presented us with significant challenges. Spectral analysis showed that the peak energy of the flare reached about 15 MeV, mega-electron volts, at the very beginning of the event, gradually decreasing over time. However, part of what puzzled scientists was the discovery of a boat-related supernova, which turned out to be surprisingly ordinary. Given the extreme nature of the GRB, one might expect its progenitor supernova to be equally extraordinary. Instead, the detected supernova turned out to be almost completely unremarkable. It even lacked signs of heavy elements, which are usually associated with such powerful explosions. But more on that later. This unexpected discovery has led to several hypotheses, one of which suggests that the relative position of the Earth to the GRB may have played a crucial role in the concentrated detection of gamma rays. The narrow jets emitted during the explosion were likely pointed almost perfectly toward Earth, making the event appear much more intense than if the jets were slightly off-axis. This alignment, combined with the GRB's power, created the perfect storm that resulted in BOAT being recorded as the brightest GRB ever observed. In addition, the detection of such high-energy photons raises intriguing questions about the mechanisms of radiation. Conventional models can't fully explain the observed unusual energy levels, leading some researchers to consider the possibility of new physics, such as interactions with dark matter particles. While these ideas remain speculative, they highlight the potential of GRB 221009A to expand our understanding of the universe in directions we have yet to fully comprehend. The formation of gamma-ray bursts is closely intertwined with the life cycle of massive stars. When a star, several times the mass of the Sun, exhausts its nuclear fuel, its core can no longer support the weight of the outer layers. This catastrophic collapse leads to a supernova explosion. But in some stars, it also leads to the formation of an incredibly dense black hole. When matter from a collapsing star falls into a black hole, strong magnetic fields turn some of that matter into narrow, focused jets that fly outward at nearly the speed of light. These jets are the engines of gamma-ray bursts, and their orientation relative to the Earth determines whether we can observe GRBs. In the case of the BOAT event, the jets were particularly narrow and pointed almost directly at Earth. Normally, GRB jets scatter somewhat as they pass through space, but in the BOAT event, the jets remained exceptionally concentrated, focusing their enormous energy into a relatively smaller area, resulting in a more intense emission. The influence of these jets extends far beyond the place of their origin. When 221009A erupted, its intense gamma rays reached the Earth and interacted with our planet's atmosphere in surprising ways. One of the most significant effects was a temporary compression of the Earth's ionosphere, a layer of the atmosphere containing a high concentration of ions and free electrons. This compression was akin to the effect caused by a large solar flare when the ionosphere is bombarded by solar particles, causing communication systems and satellites to malfunction. However, the gamma rays from the BOAT event were much more energetic than those normally associated with solar flares. The energy of the burst was enough to cause noticeable changes in the ionosphere, even at altitudes where such interactions rarely occur. Observatories around the world quickly detected these changes, leading to a flurry of data analysis to understand the full impact of the GRB on Earth's atmosphere. The data collected during this event has given scientists new insights into how such bursts can affect planetary atmospheres. especially the interaction of high-energy photons and their potential to affect atmospheric chemistry and dynamics. At the chemical level, gamma rays triggered reactions in the atmosphere that produced additional nitrogen oxide and other reactive nitrogen species. These molecules play a critical role in ozone chemistry, particularly in the destruction of ozone in the upper atmosphere. Although the exact effect both had on global ozone levels hasn't yet been studied, such bursts may contribute to local or temporary changes in ozone concentration, potentially affecting the protection of the atmosphere from harmful ultraviolet radiation. However, these observations have also raised new questions. The unprecedented strength and narrowness of the boat event jets challenge existing models of GRB formation and propagation. Standard models predict a certain degree of jet spread, which helps disperse energy over a wider area. But the boat event jets have disproved these expectations, suggesting that, under certain conditions, jets can remain tightly focused over much greater distances than previously thought. According to modern ideas, the extreme energy and rapid rotation of the collapsing star played a key role in this. The intense magnetic fields produced by the star's rotation probably contributed to the collimation of the jets, preventing them from spreading out in space. In addition, the lack of significant interference from surrounding matter may have allowed the jets to maintain their tight focus over vast distances. These findings not only challenge our current models, but also hint at the possibility of previously undetected GRBs with similarly focused jets that may have been missed by our instruments due to their directional nature. A better understanding of these mechanisms may reveal new classes of GRBs and their potential impact on both the local environment and distant planets, including Earth. However, let's return to the question of how our outburst is related to the formation of elements in the universe. It's simple. The formation of elements in the universe is history written in the hearts of stars. Inside a star, nuclear fusion works like a cosmic forge, turning light elements, such as hydrogen and helium, into increasingly heavier elements. This process continues until the element iron is formed. At this point, the fusion process no longer releases energy. It requires more energy than it produces, leading to a catastrophic imbalance. The star can no longer support its weight, leading to its eventual collapse, and often to a supernova explosion. While fusion in stars easily produces elements up to iron, much more extreme conditions are required to create elements heavier than iron, such as gold. These heavier elements are formed primarily by a process known as fast neutron capture, or R process. During the R process, the dense environment with a high neutron flux allows atomic nuclei to rapidly capture neutrons, creating increasingly heavier elements in a very short time. This process is best known in neutron-star collisions, where the enormous energy and neutron-rich environment create ideal conditions for the R process to occur. However, neutron-star collisions are not the only cosmic events that can produce heavy elements. Another potential site for R process nucleosynthesis is the collapse of massive, rapidly rotating stars into black holes, events known as collapsars. In these scenarios, intense magnetic fields and rapid rotation can drive powerful jets that contribute to the R process, potentially creating significant amounts of heavy elements such as gold and platinum. But when scientists pointed their instruments at the boat event, they were surprised to note something conspicuously missing. Despite the extreme energy and conditions seemingly ripe for nucleosynthesis in the R process, no evidence of heavy elements was detected in the supernova spectrum. No gold, no platinum, none of the things one would expect from such a powerful event. This absence raises important questions about our understanding of how and where the heaviest elements in the universe are formed. This surprising result leads to the thought that not all collapsars are prolific producers of heavy elements. Perhaps the conditions required for significant nucleosynthesis in the R process are even more specific than we thought. and may only occur under certain conditions within these already rare events. On the other hand, this could mean that other processes or conditions related to neutron-star mergers play a more significant role in enriching the universe with heavy elements. Another interesting thing about brightest of all time is that it may well shed some light on the nature of dark matter. According to one intriguing hypothesis, dark matter may consist of particles called axions, hypothetical particles that have not yet been directly observed. The idea that photons, particles of light, can turn into axions as they travel through space is a tantalizing one. If true, it could help explain why dark matter is so hard to detect. Perhaps it's hiding in plain sight in the form of photons that can turn into axions and elude our instruments. The boat event, with its intense burst of gamma rays, provides a unique opportunity to explore this hypothesis. As these gamma rays spread across the vastness of space, some of them may have interacted with cosmic magnetic fields, becoming axions. This process could reduce the flux of gamma rays reaching Earth, a subtle signal that could hint at the presence of axions. Although no definitive evidence for the existence of axions was found in the boat event data, this possibility remains an interesting avenue for further research. If future observations of such events reveal patterns consistent with the conversion of photons into axions, this could be a breakthrough in our understanding of dark matter and open the door to new physics beyond the standard model. As we look to the future of astrophysics, the study of gamma-ray bursts remains a cutting-edge frontier full of promise and mystery. Current missions such as NASA's Fermi Gamma-Ray Space Telescope and the European Space Agency's Integral continue to play a critical role in directing and analyzing GRBs. But the next generation of missions will push these boundaries even further. Projects such as the Sino-French SVOM mission and NASA's upcoming COSY mission are designed to provide unprecedented insight into the high-energy universe. These missions will aim to detect the most extreme cosmic events and will allow us to collect data with greater precision, potentially unlocking new physics and deepening our understanding of the mechanisms behind these powerful explosions. Will future observations reveal the elusive nature of axions, or perhaps identify the specific conditions under which the heaviest elements are formed? These are the questions that define the next steps in the exploration of the universe, guiding us toward a deeper understanding of the cosmos and our place in it. Events such as BOAT serve as milestones in the development of astrophysics, reminding us that the universe is much more complex and dynamic than we can currently understand. Each discovery forces us to ask new questions and propels our quest for knowledge forward. And who knows, perhaps the answers to these mysteries are just a cosmic explosion away and are waiting to be uncovered by curious minds. In the meantime, we'll continue to keep you up to date with new developments. Stay inquisitive, and until next time,